Hello everyone, welcome back to Sky Academy YouTube channel. Myself Vamsi. In this particular tutorial, we will be discussing about data structures, interview question and answers from interview bit platform. So if you don't know what is interview bit platform, so I will give you a glance about interview bit. So interview bit is a platform where you can practice coding questions which were asked frequently in an product based companies, and also you can find plenty of articles and blogs related to the tech and interview preparation tips. Okay, so in this particular tutorial we will be discussing one of the blog which was written on the data structures interview preparation. Okay, so the link to the blog will be available in the description. Please do check it out. Let me walk through you the topics that we are going to cover in this particular video, and we will be starting with the definition of data structures and where can we use data structures and what is the usage of learning data structures, and also we will be discussing about types of data structures available like trees, linked list, stack, queue, graphs. Okay, and we will be talking about each one of them in detail and writing code for defining them and how to use them and what are the applications of each of them. Okay, where can we use in a real world, so how can we build an applications using the data structures. Okay, so it's not limited to theoretical, so we will be writing plenty amount of code as well, and we will be discussing a few important aspects in the while writing the code. Okay, and a logic behind the code. Okay, so I highly recommend you guys to watch this video till the end, and if you are visiting channel for the first time, please do subscribe this channel, and if you like the video, please hit that like button up, and if you have any queries, please let us know in the comment section. We would love to answer them. So before starting the actual video, so I would like to give you a few tips for your next interview. So very first one, so if they asked you to define something like define a graph, define a tree, just don't settle for the definition. So please go on an extra mile and give them some examples, and so that they can understand the concept in a better manner. Okay, so that you can solve the real world problems as well. Okay, then the second one, it is for your DSA rounds. So if they have an interviewer asked you question, and if you know the answer for that as well, but don't directly jump to the solution. So ask them few questions, like if they have given an array. Okay, like ask them like, will there any chance of it contains a negative integers, or what if the size of the array is 0, and also what if there exists no solution for this, what should I return, like -1, 0. Okay, so please clarify all your doubts before starting a solution. Then always start with the brute force approach. Okay, which is an n square, or if it is an recursion based, n 2 power n. Okay, then try to optimize it, so like sorting, then a linear solution. Okay, so this is how our interviewers will understand that you can solve the problem with the very brute force manner to the optimized way. Okay, it involves a lot of thinking, so they want that. They don't want people who mug up the things. Okay, so before getting on to the very first question, let's try to understand what is a data structure and what are the types available in the data structure, and where we can use the data structure in the day-to-day life, and what is the usage of data structures in the current organizations. Okay, and what are the fields that our data structures has been implementing. Okay, so it's very important to understand the applications of any concept. Okay, rather than just solving few problems. It doesn't make sense if you don't know why to use data structure. Then what is the need of using data structures? Okay, so then first we'll try to understand how can we use data structure and what are the data structures available. So the very first question here is, what is a data structure? So a data structure is a fundamental concept of any programming language, essentially for algorithmic design. Okay, it is used for efficient organization and modification of data. So let me put it in a simple terms. Okay, so a data structure is data structure represents a way of organizing or storing the data in the memory, so that it will be easy for us to manage data. Okay, like manage in the sense it will be some operations like insert, delete, update, okay, kind of operations, so that we generally do perform such operations on any data, right? So here, what is the need? Okay, so what does it make sense? Like, so if I store, okay, like I will be having 10 files. If I store them in my memory, like what is the purpose? Like why we need data structures? So it is going to store in anywhere, right? So okay, if you are talking about 10 files in your mobile, it's okay. Now let me ask you few questions. Let's say, let's take an example of Instagram. So everyone uses the Instagram. Okay, let's assume one profile. Okay, one profile which has a 10K followers. Okay, or let's consider Virat Kohli's profile. Okay, Virat Kohli profile. Okay, where he will be having 150K followers. I'm not sure it's correct or wrong. Okay, I'm assuming that. Okay, let's take an example. Okay, now if Virat Kohli has posted one picture, okay, Virat Kohli has posted one picture, like post, or he has shared some story. Now it has to reach for 150 or 1 million or any number of people, right? So it has to be accessible for the 1 million people. Now, like just imagine you are storing that data in somewhere, okay, in somewhere, and whenever I have opened my Instagram, okay, if I am huge follower of Virat Kohli, since I am like whatever post he shares, I will be liking that. Okay, and among all the stories that I have been displaying on my profile, I'll be first seeing the Virat Kohli profile. Okay, in within fraction of seconds you can see that, right? So whenever someone posted, it is going to share like amount of time that I have been posted as well, like 1 second, 1 hour, or 10 minutes. So do you think this is going to come in within 1 second? You might be wondering. My answer is yes, it is going to refresh within the 1 second or 2 seconds at max. So to get the data that much faster, okay, Virat Kohli is in Mumbai. Okay, let's assume. Let's say I'm in Australia or US. Okay, then do you think it is traveling from Mumbai to US within that many seconds? No. Okay, like from Mumbai, it is storing in some, like with the help of some CDNs. Okay, it is storing somewhere in data centers, and then it is getting access in the US, okay, by using the CDN, US CDN. Like so how we are getting stored this data, that is the matter. So we need to store the data in such a way that we can access that very easily, very fast. Okay, so if you like you can easily assume that, like say, you will be storing all your books, okay, like randomly in your room. Okay, now I want to get the one book from the room, okay, where you have stored all your books randomly, okay, in some books in bedroom, some books in kitchen, some books in hall. Okay, now how much amount of time it will going to take to fetch one book, like search from one book? Now can I say that at max it is going to take 10 minutes for sure, right? Now just assume if you have stored all the books, all the books, all the books in an organized manner, in a organized manner. Now how much time it is going to take? I'm pretty much sure that, let's say, I have stored all the physics books in one rack, chemistry books in one rack, data structure test books in one rack, then it is going to take at max 1 minute. Yes, 1 minute. Okay, so there is a huge difference between 1 minute and 10 minutes, right? So even if it is not making sense for you, but a client or user who are waiting for your data will going to make, and 10 minutes of waiting time is a little hectic for them. Okay, that is the usage, that is the necessary of organizing the data so that we can easily access the things. Okay, so this is the use case that we need to learn data structure. Okay, now we have talked about what is data structure and why we need data structure. Now how many types are there in data structure? So I can say that all the data structures has been classified into two types: linear and non-linear. What is this linear and non-linear? So linear and non-linear. What is this linear and non-linear? Okay, so I can say that like if the elements of a data structure results in a sequence or linear, then it is called as a linear data structure. And when the elements in a data structure results in a way that traversal of nodes is not done in the sequential manner. Like you can easily remember this as a, whenever we are talking about this linear, we can say that storing the data in the linear manner or a sequential manner means I'll write one after one. Okay, let's say if I have stored something here, then right after that I will be storing another, then right after that, then right after that. So if I want the third one, I can easily go there. Okay, I can easily go here and pick up that. So because everything is in sequential order, they are following the order, whatever, like, so first you came, then you go first. Okay, so like that. Okay, now when we are talking about non-linear types, it is not like sequential, it is storing in non-sequential order. So what is this non-sequential? Let's say we will be storing the data structure like we can assume our file structure. Okay, file structure. Let's say I have a desktop folder. In that desktop folder I will be having let's say scalar folder, and again in scalar folder I will be having another folder called data structure, and again in data structure I will be having another folder called arrays. Again in arrays I will be storing something. So here you might think that for along with data structure there will be something as well. Let's say my computer, or let's say I have a folder of my name called Vamsi, and in scalar folder as well I will be having many things. Okay, so here the data is in not in sequential order, it is in random. Okay, and if you need something, you need to go and search every possible way. Okay, then only you will get to know where it is actually stored. So that is what a linear and a non-linear data structure means. Now we'll talk about what are the data structures that comes under linear and non-linear. So if you observe the things here, for under the linear data structures we will be having arrays, linked list, stacks and queues. Okay, we'll talk about them, each of them in detail in the further. Okay, but as of now let's remember the names. Okay, coming to non-linear data structures, we will be having trees, graphs, tables and sets. Okay, we'll talk about them, each of them for sure. Okay, please bear with me till the end. Now let's try to understand the where we use these data structures. So I've told you enough examples in the while discussing the data structure as well. Now let me put all of these things again. Like I can simply say that wherever there is something like programming, I can easily say that there is a data structure as well, directly or indirectly. If you are storing something, then directly or indirectly you will be using concept called data structure. It represents how you stored your data. That's it. Okay, and like you can see these things. Okay, so artificial intelligence, compiler design, machine learning, database design and management, blockchain, numerical and statistical analysis, operating system development, image and space recognition, cryptography. Not limited to these things. Okay, there are few more other, like even Android applications, web applications. So everything is being backed by some databases, right? So indirectly we will be using the concept of data structures in storing the data. Okay, like if you are talking about database, how we are using database. Okay, so if you are storing any RDBMS database, okay, like a SQL, now can I say that all the data is being stored in the form of tables, where you will be having a columns and rows. So can I say that this is going to be non-linear data structure? Yes. Okay, so this is how you will be using the data structure in the day-to-day life. Okay, now let's get into the some. Okay, this is what we have discussed so far, applications of data structures. And this is the most important question that everyone should have to be clear with. Okay, benefits of learning data structure. So yes, if you are a CS guy, or if you are one who is aiming for CS jobs like computer science field, then you are on the right page. You have to learn the data structures for sure. Okay, there is no middle way. And even if you consider all the high paying jobs, okay, all the high paying jobs requires or test you or ask you a data structure on algorithm questions in an interview. Okay, in an interview. So why does this happen? Because these data structure and algorithm problems involves a lot of problem solving skills. Okay, like if you are given an problem where you need to handle a 10 GB of data, okay, 10 GB of data, then how can you organize that? Okay, how can you store that in database, and how can you make it is being reasonable for everyone to access? So such kind of problem solving skills will come under this data structure. That's why companies will ask a data structures and algorithms questions in an interview. Okay, now another most question to be addressed here is data structures in C and Java. So people might be asking like questions like so which language should I pick up for learning data structures, be it C++, Java, Python, or any other language like JavaScript, C Sharp. So all I can say that is the concept is same. Okay, the basic fundamental concept of any data structure is going to be same, but it only differs in way like how you are going to store your answer, and how you are going to represent in the things in a syntactical way, and how you are converting your logical thinking to the programming. So it's, I can say that it's just an syntaxes. Okay, and that is what you need to understand. If you know, if you have the concept, then no one gonna judge you or ask you to only code in this particular language. I don't know that. Okay, so no one is gonna tell you that. So language doesn't matter. Okay, you can learn it in any language. Okay, so let's talk about this as well. Okay, so this is what we have discussed. And in an object oriented programming language like Java, data structures are being implemented using class and objects. Okay, so in object oriented means OOPS languages like Java, Python, C++, we use a concepts called classes and the objects to implement the data structures. And coming to C, which is not an object oriented programming language, we use the concepts called structures. Okay, structures and functions to implement the data structures. Okay, and I would like to tell you about this like inbuilt support of languages provided by the different languages as well. Let's say if you are a Java coder and like you wanted to use your data structures in your programming, so you might be wondering, should I learn the implementation of, like, should I manually implement all the things in the programming? No. So Java supports in Java there is a thing called collections library. Okay, where you can get all the inbuilt, okay, all the inbuilt support for the data structures. All you need to do is you need to just declare them, and you can define them and you can use them. Okay, and coming to C++, you will be having STL library. Okay, STL library, where STL will provide all the unnecessary support for your implementation of the data structures. Okay, you don't need to implement them manually every time. Okay, you can just import these either collections in Java, C++, STL in the C++, and you can use them. Okay, I think now let's get started with the actual questions. So the very first question that we are going to discuss is difference between file structure and the storage structure. Okay, so let's talk about first file structure. So a representation of data into secondary or auxiliary memory, may say any device such as hard disk, pen drive that stores data which remains intact until manually deleted is known as a file structure. Okay, it is saying that whatever the data that you are storing, okay, whatever the data that you are storing in your hard disk and pen drives, will be called as your file structure. Okay, and what is about storage structure? So a storage structure means whatever the data that you are storing in your RAM, okay, in your RAM, that is called as an storage structure. So what is the difference here? So if you store anything in the hard disk or pen drive, it won't get deleted even after you remove that thing, or if power cuts, if you face any power cut. But in case of the data which is stored in RAM, if you guys have witnessed a power cut, or if you have shut down your laptop and restarted your laptop, then you can't see the data which is stored in the RAM. Okay, that is a major difference between the file structure storage and the storage structure. Okay, now the second question. So can you tell me how linear data structure differ from non-linear data structure? So as we discussed earlier, so linear data structure stores the data in the form of a linearly, and these non-linear data structure stores the data in non-linear manner. So which is going to be either you need to traverse to all the things, okay, which is in connected way, then that's how you can access them. Okay, so if you observe in this particular diagram, so this is called as an storing the data in the linear manner, means sequential manner. If you observe, so okay, like you can traverse through these elements using one single type. Okay, what is a traversing? Okay, what is a traversing? So basically, let's say you have an array. Okay, if you don't even know what is array, just tick. Okay, like if you have something like this, and you have some data here, 1 2 3 4 5 6 7. Now a traversing means visiting all these blocks. Okay, you can consider this as one block, this as one block, this as one block. Okay, so traversing means you need to visit all the blocks at once at least. Okay, now so if in the case of linear data structure, you will be starting from 1 and you will be coming to 2. From, like, you can't go to 3 here. Okay, so if you are traversing in a linear manner with the speed of 1, and you from here you can go to 3, then 4, then 5, then 6, then 7. So it is going to be linear in fashion, right? But if you consider this, okay, like it is starting from the A, and from A you will be let's assume this things are being represented as a connection. Okay, connection means you can, from A you can go to B, from A you can go to C or E as well. Okay, if there is exist a path. Now from A you will be having 3 choices. Okay, from B again you can go to E or B, A again. So here it is not sticking to one structure, one sequence order. So you can go to any order that you want. Okay, but in case of linear, you can only move to the next thing. Okay, that is in sequential manner. Okay, so that is what a difference between sequential and non-sequential is. Now what is an array? An array is a collection of similar type of data stored in a contiguous memory location. What is a contiguous memory location? Let's say, okay, so this is an array. Okay, and my first element, okay, I have started at the address of 100. Okay, address of 100. Let's say I have stored 20 in it. Then I can say that I am storing all the integer typed values as of now, and I know that integer takes 2 bytes of memory. Okay, integer takes 2 bytes of memory. It means that, so it will assume like it will take 2 bytes. Okay, if it has started at 200, if it is taken 2 bytes, then the next bit will start from 1 or 2. So, and I will be storing another 10 over there, and again I am pretty much sure that it is going to take only again 2 bytes. Okay, so I will be going to 104, and then again I will store another integer and it will take another 2 bytes, so 6. Then I will be storing 3, again it will take 108. Okay, now again I will be storing 1, so it will take 110. So here everything is in sequential order. Now what is an array here? Like what is the uniqueness of the array? So here if you observe, we will be storing all the integer typed values only. Yes, because in an array you are allowed to store only one type of data. Okay, whatever you have defined it. Now what is it? Defining an array, okay, or declaring an array. So declaring means you need to, if you wanted to use any variable, you need to declare that first. Okay, how can we declare the int like array? So let's say I have a variable called arr which represents the array, and this symbol will help us to tell this particular thing is a array. Okay, means it is going to store the data in the sequential order. Okay, and it will take multiple values at the same time as well, which are int types. Okay, only int types. Now if I have represented it as a something like character array, okay, if I have defined it as something like this, then it will take a characters, okay, one character at each time. Okay, or only it supports only character or either integers as well, because in C language or in C++, all the characters and indirectly equal to the integers until 256. Okay, and all the numbers until 256 is going to indirectly represent the characters because of the ASCII values. And if you don't know what is ASCII values, please have a look at that. Like just go to Google and search for this and you will find what is ASCII values. Okay, now let's move on to the next question. What is a multi-dimensional array? Okay, so we know that array stores in the data of this manner. Okay, the address might be 100, 102, 104, 108, 110, 112, 114 at last. Okay, now what is this multi-dimensional array? So a multi-dimensional array means, so I can say that, so if you observe this carefully, I can say that it has one row and 1 2 3 4 5 6 columns, right? One row, 6 columns. So this is a single dimensional array. So whenever you will be having one row, okay, one row, then it is called as a single dimensional array. So whenever you will be having multiple rows, okay, whenever you will be having multiple rows like this, okay, it is called as a multi-dimensional array. So again it is going to call, like if you observe this thing carefully, it is in the form of matrix, right? So if I represent this in the matrix, so it will be having 3 rows and 6 columns. So 3 into 6 matrix. Okay, so I can say that 3 rows, 6 columns. Yep. Now here at max, how many elements that you can store here? I can say that you can store 6 elements. Okay, 6 elements. Now here you can store at max 18 elements. Okay, 18 elements. So you might be wondering like how to access these elements. Okay, so for that we will be having a concept called indexing. What is this indexing? So basically, let's say we will be having an array with the size of 6. Okay, size of 6. So 1 2 3 4 5 6. Okay, so size of 6 means it can store a 6 values or 6 elements at max. Okay, so if I represent these things in the integer or like indexing, then it is going to start from the 0, then 1 2 3 4 5, and for for every array the last index is going to be size minus 1. Okay, and it will start from the 0. Okay, start from the 0. Now let's assume here we will be storing a 10 20 30 40 50 60. Now how can I access these elements? And let's assume the name of this array is ARR. Okay, now if I write ARR of 3, okay, if I write something like this, now we will be getting output as a third index value. Okay, in ARR, okay, array, the third index value. So what in ARR, what is the third index? This is the third index. Now we are going to get the 40 as our output. If I write ARR of 1, what does it mean? It means that in ARR variable, okay, array, we need a 1th index. So we are going to get the 20 as the output. Now if I try to access array of 10, what are we going to get? We are going to first check, is there any index with the number of 10? No, there is no index such that. Now it is going to throw an error or exception. If you are an Java or Python guys, it will throw an exception which is named as a array out of bounds exception. Array out of bound exception. Okay, which means that the index which you are trying to access is not there. Okay, not there. That's it. Now this is okay for this single dimensional array. How can we access the multi-dimensional array? Okay, multi-dimensional array accessing. How can we access that? So in the case of 1D dimensional array, we will be having only one row and n columns, so we can just represent in one index. Okay, but in case of a multi-dimensional array, we will be having something like this. Okay, now let's try to represent these things in rows first. So it is going to be 0 row, 1 row, and second row. And if I represent these columns, 0 column, first column, second column. So it's just as representing the things in the matrix. Okay, represent the things in the matrix. Now, so if I want this particular element, I can represent it as 0, 0. Like let's say if this is an name of array. Okay, this name of array, then I can say that array. First I need to mention the row which is an 0. Then I need to mention the column which is again to be 0. Okay, the first 0 represents the row, second 0 represents the column. Okay, if I write 2 of 1, which means a second row, this second row, and first column. Okay, this is, now I am going to get this particular value. Okay, so this is how we are going to access the we can access the elements in a multi-dimensional and single dimensional arrays. Okay, now what is a linked list? Okay, linked list is another data structure which follows a linear data type. Okay, so a linked list is a data structure that has sequence of nodes where every node is connected to the next node by means of reference pointer. Okay, we'll talk about that later. Now elements are not sorted in adjacent memory locations. They are linked using pointers to form a chain. Okay, and each node is having data field and the reference pointer. So if you observe this particular diagram, we will be if you consider this as a node, and at the first half we will be having data, and the second half we will be having the pointer to the next node. What does it mean? Okay, let's say, okay, this is our node. Okay, this is our node, and node has two parts. One is data, another one is link to the next node. Okay, so this data represents something, let's say 10. I wanted to store that 10. Now what does this part is going to store? I can say that this part is going to store, let's say, okay, let's come to let's try to define a few other nodes as well. Okay, now this is storing 20, this is storing 30. Now this node is being stored in the memory location of 200, and this is being stored in the memory location of 500, and this is being stored in the memory location of 1000. Okay, now I wanted to go to 20. Okay, I wanted to go to 20 after the 10. Okay, I wanted to go to 20 after the 10. So here I need to mention the node address which I would like to go next. Okay, so I wanted to go to the 20. So what is the address of the 20? It is a 500. So I will mention 500 here. Now after 20 I would like to go to the 30. Okay, 30. Now what is the address of the 30? It is going to be 1000, right? So after 30 I don't want to go anywhere. Okay, I don't want to go anywhere. So now it is going to store the null. Okay, which means that if you would like to not to go anywhere, okay, after visiting some node, okay, then you need to point that as a null pointer, okay, which represents this is the ending point, okay, which is the ending point. And every starting node will be having a head node, okay, which represents the starting point of a node. Okay, done. Okay, this is how a linked list is being represented. And if you observe the data, everything has been stored in the form of sequential. Okay, after 1 we will be storing, like, going to the 20. So here we will be just directly representing the things in the form of memory location. Okay, we are not going anywhere, we are directly going to the 500 after 200. So that's what it is in sequential way. Done. Now let's go. Are linked list of linear or non-linear type? Okay, good question. We have seen the answer just now, right? Linked list can be considered both linear and non-linear data structure. This depends upon the application that they are using. Okay, so this can be treated as a both linear and non-linear, but moreover it depends upon the where we are using the context where we are using that term called linked list. Okay, so when linked list is used for accessing strategies, it is considered as a linear data structure. When they are storing data storage, it can be considered as a non-linear data structure. Okay, so it totally depends upon the application that we are using this linked list. Okay, now let's move on to the next question. So how are linked lists are more efficient than arrays? Good question. Okay, so here I would like to mention the term called time complexity and space complexity. Okay, so whenever you are writing an program, or whenever you are writing an algorithm, okay, so these are the two aspects which talks about whether your code which you have written is an efficient or not. Okay, so if it is taking minimal amount of space and time, minimum amount of space and time, it can be called as an efficient algorithm for a problem. Okay, like even in the case of real world applications, let's say you are using a payment. Okay, you are let's say Amazon. Okay, Amazon website, you have bought one product. Okay, you have bought one book, let's assume. Okay, one book, and now you are paying amount for this. Okay, you are doing payment. So you just imagine if your payment took 1 minute of time to finish. Okay, 1 minute of time to finish. How do you think? No, yaar, I won't. I am not interested in doing the paying the online. Okay, because it will take 1 minute of time, and until that you receive the done. Yes, payment has been received. Your order has been successfully placed. You won't be in a peace, right? It is always like lub dub. Your heart will be like pumping up. Okay, so what if my amount got detected from the account, and if my order is being cancelled? So you might be having these things until you have seen the payment has been done. Okay, so in that case it should be done in the either 1 second or 2 seconds of time. Okay, then only people will go and purchase the things from the Amazon website. Okay, so in this case it is an time complexity. So 1 minute of time complexity and 1 second of time complexity, which one do you prefer? The answer is up to you. Okay, and that is the answer for the time complexity as well. Okay, now let's come to the question. So insertion and deletion operations. So basically what is this insertion and deletion? So insertion and deletion process is expensive in an array, as the room has to be created for the new elements and existing elements must be shifted. Okay, let's say we have an array something like this. Okay, you will be storing 1 2 3 4 5. Now I would like to, okay, in between 3 and 4 I would like to insert the 6. Okay, like I'm expecting my end array should be looks like 1 2 3 6 4 5. Now like to perform this operation, what is the process? First we need to create this 6. Yes, we need to create this 6. Then we need to replace this. Okay, we need to put this here. Okay, to put that here, is that as simple as that? No. So at first we need to create a space here. Okay, then we need to move the 4 to the 5th position and 5 to the 6th position, right? So we have created the room here, and then we have shared, like we have shifted 4 to the next guy and 5 to the next guy. Then we have replaced 6 over there, like so. Here to insert one element we are doing 3 operations. Even for delete, if I wanted to delete that, okay, if I wanted to delete that, first what I need to do, I need to delete this 6. Okay, I need to delete the 6. Okay, then I need to move my 4 to here and 5 to here. Again it's taking 3 operations, right? So which is an like complex thing to understand. But in case of linked list, let's see, I have a linked list something like this. Okay, 8. So I have linked list something like this. Now I would like to insert 9 here. Okay, 9 here. Now how can I insert? So it's just simple, right? So I will break this point. Okay, connect a 2 9 after 7, and I will connect 8 after the 9. That's it. It's as simple as that. We don't need to perform any replace operations or move operations here. We are just deleting the, like we are just breaking the bond over there and connecting the bond to the 9. That's it. Okay, it is as simple as that. Okay, and it is going to take the big O of one complex. And if you don't know what is time complexity and space complexity, I highly recommend you guys to watch the tutorials which are being already created on the time complexity and space complexity in this particular channel itself. Okay, so there is a playlist called DSA. Okay, you can go there and you will find a plenty amount of videos over there. Cool. So this is about even if I take a deletion operation, let's say if I wanted to delete this 9 itself, now what I can do, so I will simply break this out and I will connect to 8, and I will break this out and I will delete that. That's it, as simple as that. Okay, we are not doing any complex operations like move and all. Okay, it's very simple. But I would like to talk about something like accessing as well. Okay, accessing as well. So to access an array elements, it is going to be as simple as that. Okay, you will put your index value and you will get the value. So it is going to take constant like time. But if I wanted to access the linked list elements, it is not as simple as that. Okay, if I want to access this particular element, first I need to start from the head. Okay, I need to start from the head. I need to go to every node. Okay, every node until I found a node which I want. Then only I can access that element. So I can't go in the middle and I get that. Okay, I need to start from the starting position. I need to go to the every node and I need to check. Okay, yeah. So the second thing is dynamic in nature. Yep, dynamic in nature. So point to be discussed. So here, what is a dynamic in nature? So basically there were two things, static and dynamic. So static means, let's say if you are defining an array, you will be mentioning how many number of columns that you need here itself. Okay, here you can't modify this in later part. Okay, you can store only 5 elements. It is defined, it is fixed. Okay, but in case of dynamic, you will be giving only like the number of elements, okay, that you required. Okay, let's say, so you have, in the case of static, you have defined 5, but later you observe that you will be requiring 10 elements to be stored. That in that case it won't support. Yes, Yes. Now let's say this is first point, and second point is, let's say you would like to store the two elements. Okay, you have defined 5, but I found that I only require 2 elements. In that case, 3 space is waste. Okay, the space for 3 elements is waste. Okay, you are not using that, right? But in case of dynamic, let's say you will be defining the amount of memory or the amount of elements that you would like to share. Okay, then only you can create the things. Okay, let's say if I want a requirement of 2 elements store, then I will create a 2 elements. If I requirement of 100, I will create 100. That's how it works, right? So this is about a static and dynamic. Okay, and in case of linked list, it's always a dynamic. It always dynamic in nature. Okay, it is always in dynamic in nature. There is no boundaries for that. But in case of arrays, while defining the array itself, you need to mention whether like how many elements that you are going to store. Okay, so it is one of the drawback for array. But how can we make this as a dynamic? So there are few concepts, okay, known as malloc, so which helps us to define the memory or allocate the memory in the dynamic space. Okay, while runtime. Okay, you can call this as a runtime. So basically we will be having two things, compile time and a runtime. What is this compile time? So compile time means after writing the code, okay, after writing the code, you will be putting the things. Okay, like let's say while writing the code itself, you will be mentioning the things. But runtime means after compiling the program, okay, based upon the user's requirement, the coding has been changing. Okay, that is called runtime, during the runtime. So as we discussed, it's a memory wastage as well. So if I have defined 5, if I have used only 2, then it's a memory wastage, right? So that is what it is discussing about. Now let's move on to the next question. So explain the scenarios where you can use a linked list and arrays. Okay, so I will like leave this particular question to up to your imagination. Okay, in total. Okay, we have seen hell about these things. Okay, where what are the different types of linked list are available, and different types of arrays available, what are the drawbacks here, and what are the cons and pros of arrays and linked list. Now just imagine, okay, so just take out just go through this and just try to imagine whether we can apply a in this particular situation, can we apply array or linked list. Okay, so I will just go walk through these things. Okay, so following are the scenarios where you use linked list over array. Okay, so when we do not know the exact number of elements beforehand, so as we said, there is no boundaries for linked list. So it is means that you can, like, if we don't know the requirement, we can go with linked list. So whenever something has been changed, we can append those changes. But in case of array, we can't do that. So when we know that there would be large number of add or remove operations. So as we discussed, linked list is very easy to perform insert and deletion operations when compared to the arrays. So in that cases, we can prefer linked list. So less number of random access operations. So random access operations means a searching. Let's say we have different nodes and I wanted to access this particular node. Okay, so I can't easily go to this particular node directly, right? So I have to start from the starting, then I can go to each one manually. Then only I can access that element. So in that case, let's say if I have 1000 nodes, I wanted to access the 999 node, then how many nodes I need to check? I need to check 999 nodes, right? So it is going to be little complex operation. So in case of array, I can easily say array of 999, then I will get the answer. Okay, in such cases, so like if it has a very less number of random access operations, then you can prefer linked list. Then when we want to insert items anywhere in the middle of the list, such as while implementing the priority queue, linked list are more suitable. So we'll talk about these priority queues later. Okay, so as of now, they are saying that if you wanted to insert something in the middle, as we discussed earlier, So in that case, you can prefer linked list over array. Now what is the second thing? So below are the cases where we use array over the linked list. So as of now we discussed about using linked list over array. Now let's discuss about using arrays over linked list. So when we need to create index or randomly access element from the frequent like more frequently. So as I said, if we wanted to access 999th index, we can simply say ARR of array of 999. So you can access the thing very easily. Now the second point, when we know the number of elements in the array beforehand in order to allocate the right amount of memory. So as we discussed earlier as well, so if you know the requirement exactly, let's say if I wanted to have only 20 elements in my array, then you can go with this particular arrays. Okay, if you are not sure about how many elements that are going to are required, then you should go to the linked list. Third thing, when we need speed while iterating over the elements in the sequence. So speed matters a lot, right? So that as speed directly depends upon the time complexity. So if you are going a little faster in the your memory, then like in your array, then your overall time complexity is going to be little faster and efficient. Yes, so this is about scenarios where we prefer either linked list or arrays. Now what is a double linked list and what are its applications? So till now we have talked about single linked list. Now let's talk about double linked list. So in single linked list we will be having only the pointer to the next node. Okay, the pointer to the next node. So just imagine if you have a pointer to the next node and the previous node. Okay, the previous node, then this is called as a double linked list. Okay, so here your node would be containing three parts. One is data and the next pointer and the previous pointer. Okay, and the previous pointer. So this is what a double linked list means. Let's coming to the applications. So here, so applications of DLL. So a music player list with the next song and previous song navigation options. So everyone loves music, right? So if you have opened any music player, okay, if you have opened any music player, you could have observed next pointer let's say so if you are listening one music, okay, there will be options, right? Like go to the next song, go to the previous song and pause the song and resume the song. So something like this. So here, so you can assume that this going to the next song is a next pointer, going to the previous song is a previous pointer. Okay, this is one use case where you will be using double linked list. And the browser cache with the back forward visit pages. Okay, so let's say I have currently opened Google Chrome. Okay, like interview bit blogs website. Okay, interview bit blogs website. Now like before coming to interview bit platform, I have opened a SCALER Academy website. SCALER Academy website. Okay, now before back, okay, so like after visiting interview bit as well, I have visited another website, okay, which is called as let's say SCALER Forever website. Now I am currently in the interview bit platform. If I wanted to go to the web page or the website which I have opened before to the interview bit, then what can I say? So here you can see these navigation buttons, right? Navigation buttons. So this one represents the backward, this one represents the forward. So this is the current page which I am in, so interview bit. Now if I click on this back page, I will go to the SCALER Academy. If I click on this forward page, I will go to the Forever, SCALER Forever, right? So this is one use case where we will be using double linked list. Now undo and redo functionality on platforms, right? So let's say like you have opened a notepad, okay, notepad or Word or whatever it might be. So you will be pressing Ctrl Z, right? So Ctrl Z will get the recently deleted the values. So and something so there is something like redo as well. So redo means you have like entered something and you have given a backspace, like deleted them and you wanted to get back down. So undo and redo. So these operations will also take a double linked list. Okay, so this is about double linked list and applications of a double linked list. Now, what is a stack? What are the applications of a stack? So here this particular diagram represents the enough explanation. I don't need to explain it manually. Let's say, so let's consider this particular bookshelf. Okay, now what do you think about this particular book? So can I say if I have 10 books, okay, I wanted to put them in a one rack. So all I can do is first I will put the one book, okay, this book, then I will put this book, then this, then this, then this, then this, then this, right? So I will put all of them. And if I wanted to take the, okay, if I wanted to take the one book which is on top, what it would be? It is this particular book. When I inserted that the last. When I am taking that out, the first, okay, last inserted, first taken. So this is called an LIFO. So whatever element which has been pushed into the stack, okay, at first is going to take out as the last. Okay, so stack linear data structure follows the last in first out approach. So if you even sees this, first I have pushed 1, then 2, then 3, then 4. Okay, if I wanted to take one element, okay, if I wanted to take one element from the top, okay, it is going to be 4, right? It is going to be 4. That is what a pop. So basically stack has 3 operations primarily. One is push, pop and top. So push operation helps us to insert the elements into the data structure, and pop operation helps us to delete the topmost element which you have in case of a stack which you have recently added. So here the recently added element is the 4. So when I say pop, 4 is going to be out. Okay, so the top, so this top is going to give us the topmost element. So what is the topmost element? I can say that a topmost element is the element which is been added recently. Okay, which is been added recently. So 4 is the last element that I have added recently. Okay, hope you have understood the stack and stack operations, right? So if you want in detail, like let me put here. So let's say I have these elements 1, 2, 3, 4, 5, 6. Now I wanted to put all of these elements in a stack. So okay, let me put the operations. Okay, I have operations like this. So first push 1, then push 2, then push 4, then push 3, then pop, then pop again, then top. Okay, before coming to top, let's say push 10. Okay, now let's see. So this is our stack. So what is the first operation? It is saying that push 1. So if I push 1, it is going to store something like this. Now again it is saying that push 2. Okay, 2. Now again it is saying that push 4. Now again it is saying that push 3. Now it is saying that pop. So what does pop do? Pop will delete the topmost element which you have added recently. What is the element which I have added recently? It is the 3, right? It is the 3. So I will remove that. Done. Now what is the next one? Again it is saying that pop. Okay, pop. So I will, now what is the top element? It is 4, right? So I will remove this as well. Now what is the operation? It is saying that push 10. Okay, so I will push 10. Now it is saying that top. Okay, so what is the top? So top will give you the topmost element which you have added recently. So it will give the 10. Done. So if you like top, don't delete the element. Okay, it will give you the only topmost element. Only pop will delete the element. Okay, So here these are the applications of the stack. So we'll talk about them as well now. So first is check for balanced parentheses in an expression. It's going to be one of the interesting problem in DSA. So like where you will be given parentheses like this. Okay, you need to check whether for every opened parenthesis there exists a closed parenthesis. That is the problem statement. So you can solve this problem using stack. So give it a shot. Okay, give it a try. And evaluation of postfix expression. So there is three things. Okay, prefix, postfix, and infix. Okay, so like these operations are like if you have given a plus b plus into c minus d, you need to convert this into these three operations. Okay, so in one such operation for postfix you can use the stack. Okay, you can use the stack. And a problem of infix to postfix conversion and reverse string. So a reverse string means you will be given a string. Okay, you will be given, let's assume, string like this, and you require to reverse this entire string. So how can you do that? So let's say you have a stack like this. So I will start from the first element. Okay, and I will push everything to the stack. So V A M S I. So once I'm done, now I will take the top and I will delete it, the particular top element. Now if I say top, I will get the I and I will delete this. I will pop out this I now. Now I will again say top and I will delete the pop the top. Now again I will say top, I will get the M and I will pop out. So I will again say top, I will get the A and I will pop it out. Now again I say top, I will get V and I will get top popped out. So if you see, there is nothing in the stack. So and if you see the output, I got the reverse of a Vamsi. That's how it should work. Okay, so what is a queue? So then the name only suggests that what is a queue. Okay, so just guess. Okay, so a queue is a linear data structure that follows a FIFO, first in first out. So what does it mean? So if you see, okay, like they have given one amazing example here. So you have in a movie mall. Okay, you have went to the movie theater. Nowadays everything is online booking, but just imagine, okay, like and 90 kids can imagine this. So there is a movie ticket counter. Okay, you need to go to the queue and you need to collect the ticket. Okay, buy the ticket from there, then only you will be entered into the theater. Okay, so now just imagine, so who is going to be the first person at the counter? Whoever come to the counter first, they are going to be at first. So who is going to get the ticket at first? The person who entered first. Then so who is going to get the ticket at the last? The person who entered into the queue for the last, right? That is how it works, right? Now let's say I have a few operations that we have taken out there. For queue, we will operations have NQ and DQ. Okay, we call this. So NQ will do like something like insert, what we did for push, and DQ will do deletion of top element, and a front will give you the topmost element. Okay, like the one which is very close to the counter here. Now let's say if I give the operations like NQ1, NQ3, DQ, a top, NQ5. Okay, now so just imagine this is a queue. Okay, this is a queue, and if I have, like, first I have NQ1, so I will put 1 here. Then I have NQ3. Now I have DQ. So when I say DQ, what is the element that I am going to get the out first? The one which is entered into the first. Okay, in this case the element which entered the queue first is the 1. So I will remove the 1. Done. Okay, now I have top. So what is the top element now? Say 3. Okay, after 1 has been deleted, 3 is the top, it will get 3. Now again I say NQ 5, so I will say 5. Okay, this is how it should work. Now if I again DQ, what is the element that I am going to get? So it's a 3, right? So this is how Q should work. Now what are the applications of Q? That the applications of Q. So CPU scheduling task, a BFS algorithm to find shortest distance between two nodes in a graph. So if you don't know what is BFS and graph, don't worry, you are going to learn in this particular video itself. So please watch this video till the end. Website request processing, used as a buffers in applications like MP3 media, CD player, etc. Managing an input stream. So these are some of the applications where we use Q. So let's move on to the next question. How is a stack different from a queue? It's very silly question. We have discussed so far. Okay. So a stack follows LIFO manner, last in first out. Queue follows first in first out manner. Okay. So that is the only difference between stack and queue. Explain the process behind storing a variable in memory. Okay, so they are asking us to tell the process how the data has been stored in the memory. Okay, like some variable, take out one example as a variable, then tell me. So at first variable is stored in memory based upon the amount of memory that is needed. So here like say variable is declared as an integer type, a float type, a string type. Okay, so it depends upon the type of the data that we are storing under one particular variable. So following other steps are followed to store a variable. So the amount of memory is required is assigned first. So in case of int, we will be requiring 2 bytes. In case of float, we will be requiring 4 bytes. In case of string, we will be requiring the amount of characters it has. Okay, so each character will have 1 byte. So it will be required the amount of characters it has. Then that's done with the first. Then it is stored based upon the data structure being used as well. Okay, so here let's say if we have defined integer typed array, so it is going to require a contiguous memory locations, right? So it is not about one particular starting point. It is about like sequence of operation. Let's say I have given 10 as my memory elements, then it should assign 20 amount, okay, like 20 bytes of amount for that particular array. So it should search for 20 bytes. When wherever there is a possibility of assigning 20, then it will store there. But in case of linked list, it always finds the large amount of space because it is dynamic in nature. Okay, so requirement is not stated in the before assigning the things. So it depends upon the data type as well. Let's see how to implement a queue using a stacks. Okay, so how can we implement? So we are asked to implement queue using stack. So yes, we can use there is two methods. One is using one stack, another one is 2 stacks. So as of now we are sticking to this particular approach. Okay, and maybe in some other tutorial we will try to focus on how to implement a queue using single stack as well, but as of now let's try to implement the using 2 stacks. So first, so we know that stack operations are push, pop and top, and queue operations are NQ, DQ and let's say front. Okay, so now using these operations and 2 queues, we need to implement these operations, okay, which is for queue. Okay, so first let's try to understand what are the operations and how it is gonna work. So let's say stack works in this particular manner. Okay, when I say push, okay, push 1, okay, and push 3 and pop. So pop means whatever the element which has been inserted into a stack at the last, that is going to come out at the first. Okay, so this is going to eliminate it. Done. Now again I can say top. Now if I say what is the topmost element now, currently it is 1, so I will get a 1. If I perform the same operations like NQ1, NQ3, DQ and friend. Okay, now how it should looks like, let's say, so NQ1, yes, 1, and NQ3, 3, and it is saying that DQ. So what is going to happen? So first in first out. So what is the element which has been entered into queue for the first? 1. So it is going to be eliminated. Now if I say friend, what will be my output? It would be 3. Right. So now you got what is the operations of stack and what is the operations of queue. Now let's try to implement the queue using a stack. Okay, so for that we will be taking 2 stacks. Okay, like this: stack 1, stack 2, stack 1 and stack 2, and we are going to perform this series of operations like this: NQ of 1, like NQ of 2, NQ of 5, DQ of DQ, that's it. Okay, so DQ and a friend. Okay, these are a queue operations. Okay, whenever I do NQ, it is going to push. Whenever I do DQ, it is going to be pop. Whenever I do friend, it is going to give me the top. Now let's try to perform these operations by putting this as a reference. Okay, at first it is saying that while a stack not is empty, so here stack is empty. So what we are going to do, so like first we are going to perform NQ operation, which is a push. Okay, so we'll take this and we'll call this NQ, and we say that while stack 1 is not empty, so here stack 1 is empty, so simply we are going to insert this, push this 1 to the here. Done. Now again we have seen the NQ of 2, so here this time our stack 1 is not empty. Okay, stack 1 is not empty, so what we are going to do, so push everything from stack 1 to the stack 2. So whatever we have in stack 1, we are going to pop out them one by one and push it into the stack 2. Now here we'll pop out this 1 and we'll push it into the 2. Now push data to the stack 1. So what is the data here? 2. So we'll push it here. Now push everything back to the stack 1. Okay, so we'll pop this here and then we'll push whatever we have popped to the stack 1. Done. Done. Now again we have seen the NQ of 5. So again stack 1 is not empty, so push everything from stack 1 to stack 2. So whatever we have in stack 1, we need to pop them, each one of them, and push it to the stack 2. So if we pop everything, so first I will pop a 1 and I will push it to the stack 2, then I will pop the 2 and push it to the stack 1. So first 1 then 2. Now it is saying that push a data to the stack 1. So what is the data? It's a 5. So I will push here, and again it is saying that push everything back to the stack 1. So whatever we have in the stack 2, we'll pop that each and everything, like every element, and push it back to the stack 1. So here first we'll pop 2, and then we'll push it here, and then we'll pop the 1 and push it back here. So it is going to be looks like this. Now DQ. So DQ means a pop operation. So in queue, how it is gonna work? So whatever you have pushed at the first, okay, then it is going to come out of the queue for the first. So in this case, let's say we have called DQ, okay, and if stack 1 is empty, then error. So here stack 1 is not empty, so pop an item from the stack 1 and return it. Okay, so they are saying that pop the item from the stack 1. So if I pop, what is the element? So we usually stack eliminates the last in first out. So here last has been entered this. Now I will pop this out and I will say here, okay, for this we got the answer as 1. So in this case, 1 is the first thing which has entered into queue, right? So that is what we got. Done. Now DQ. So again DQ. So what is the same? So again stack 1 is not empty. What we will do? We will do pop the stack 1 element. So if we pop, we will get 2 and return the 2 here. That's it. Now they are saying that friend. So we will be getting the topmost element. That's it. So here we have only 5. Return that. So this is how we are going to implement the queue using 2 stacks. Okay. And there is another method. So here we will be making NQ operation little complicated. Yes, right. So we are performing swapping operations, and then we are putting back to the queue stack 1, and we are making NQ operation little complicate, but DQ operation is doing in some constant amount of time. So the another approach follows making an NQ operation little easier and DQ operation little costlier. That's it. Okay, so just follow these steps. Okay, I am pretty much sure that you will be able to do this. Okay, now let's go. So the next question is, how do we implement stack using queue? So this is the opposite, reverse. Okay, so earlier we have done queue using a stack. Now they are asking stack using queue. Okay, so now we need to do this. So again we are going to use a 2 queues, 2, and we know the operations of queue, right? So first in first out, and stack is last in first out. So we need to implement these operations. So these are the sequence of operations that we can follow here. Okay, so let's try to check, okay, whether we can able to do this or not. So let's take 2 queues, q1, q2, and I will take a sequence of operations. Let's say push 1, push 3, push 5, push 6, pop, pop, top, and push. Okay, let's make it little complicated. Okay, now let's do this thing. So first step, push 1, so it will come here and enqueue the data to the q2. Okay, I will be putting it 1 in the q2. Let me change the color. Yeah, now dequeue elements 1 by 1 from q1 and enqueue it to the q2. So here currently q1 is empty, so we are not going to do this step. Now swap the names of the q1 and q2. Okay, so swap the names in the sense like whatever we have in the q1, let's put them to the q2, and whatever we have in q2, we will be putting them into the q1. Okay, so here if we do that, like it can be simply changing the names as well, so we can do that as well. So q2 and q1, done. Okay, again we got a push 3, so push 3. So first thing, enqueue to the data to the q2. So here we have q2 as here now. So dequeue elements 1 by 1 from the q1 and enqueue to the 2. So here we will be having only 1, so we'll pop this out and put it in the q1. Now swap the names of q1 and q2. So swap the names q1, q2. Now we'll follow this. So push 5. Okay, push 5. So I'm going to push it here. Okay, I'm going to push it here, and sorry. So I need to do this here. Sorry. So dequeue elements by 1 by 1 and put it back into the q2. So here, what is the element that first has got into the q1? It is 3, right? So I need to pop that of 3 first, and I will push it back to the here, and then 1. Done. Now swap the names of 2. So it is going to be q2 and q1. Done. Now again push 6. So I will push 6 in the q2 and then pull out all of these things and then put it back here. So if I pull out all these things, it will be looks like something 5, 3, 1. Right, what is the element that first got entered into the q1? It's a 5, so we have to pop that out first and we need to put it in q2. Okay, now again same, right? Now they are saying that pop. So pop, so we'll come to here. Okay, we'll come to here. So we did not swap the things. Okay, so we'll swap the q1 and q2. Now they are saying that pop, so dq from the pop q1 and return it. So what is the element if I pop it from the q1, like if I dq from q1, what is the element that I get? 6, right? Why 6? 6 is the one which has entered into the queue for the first. So if I dq, I will get the 6. So yeah, yes, so this is what I want, right? So if I am doing stack, so I will be getting last in first row. So what is the last element that got into the queue? So 6, right? So I will be getting 6. That's it. So we can eliminate this 6 now. Now again we have pop. Now what is the element that I get? So 5. So I will get a 5. So I will eliminate the 5 here. Now what is the element? Top. So what is the topmost element currently? It is 3. So I will get a 3. Now again saying that push 2. So first I will put it into the q2. Then I will pop out everything from the q1. So if I do pop out, I will get 3 and 1. And then I will be eliminating here. And then just swapping the names. So it is going to be q2 and q1. Okay. That's it. If I perform pop now, I am going to get 2 as my answer. Done. So this is how you can implement the stack using 2 queues. Okay. So I'm not writing the code here. Okay. I hope you can able to do that here, and we'll do a separate video on that as well. Now let's move on to the next question. What is hash map in data structure? So hash map is being called as an different names in different programming languages. Let me put it here. So in Python, we use a dictionary. Okay, in C++, we use a map or unordered map. Okay, and in Java, we use hash map. Okay, so the operations is same. Okay, the operations are same, and the names only different while changing to the language to language. So a hash map is a data structure that uses implementation of hash table data structure, which allows access of data in constant time complexity if you have the key. So basically, let me tell you how the data has been stored into the hash map first. So hash map follows 2 rules: key and value. So what is a key and what is a value? So a key is a unique value. Okay, a key is a unique value, so which helps this particular thing to the identify the data from the or access the data from the map. So let me take one simple example. So let's say you will be given an array of elements. Okay, array of elements like this, and now you need to calculate the frequency. Okay, frequency of each element. Okay, frequency of each element. Now how can you do that? So by using the hash map, we can do that easy. So let's say first I will check whether 1 is there in the queue or not. Okay, like hash map or not. Yes, 1 is not there, so I will put 1 and I will make sure value is assigned to the 1. Okay, so what does it mean? So till now 1 has been occurred only once. Okay, now again I can see that there is a 1. So here first I will check whether 1 is there in my hash map or not. Yes, 1 is there. So what does it mean? What does it mean? So it means that there is already exist a 1 which has occurred for once. Okay, now what do I need to do? If I can simply update this value, then my job is done. So here key is element and value is frequency of that particular element. Done. Now again I have 1. Okay, now which is like already have 1 in my map. So what I need to do, I need to just increment my value. So if I do that, it will become 3. Now I have 2. So 2 is not there in the map, so I will create 1. Okay, done. Now again I have a 2, but I have already 2 is exist in my map. So what I can do, I can simply increase the value. So now it is a 3. So whether 3 is there in my map? No. So I can just say 3 to the 1. Now the next element is 4. So 4 is not there in my map, so I will increment it back. Now I have 2. Okay, I have 2. So but already 2 is exist in my map. So what do I need to do? I need to simply increment the value of the key value of the 2. Done. So now let's cross check the things. Okay, here I have an array size of the 8. So 3 plus 3 plus 6, 6 plus 1, 7, 7 plus 1, 8. So 8. Done. So this is the frequency. So this is how we store data in the hash map. So what are the things that you have identified here? So in hash map, we can't store the duplicate values. Okay, we can't store the duplicate values. Yes, and if we can't store the duplicate values is an passive statement. Okay, what we can say is it will get overridden, that's it. Okay, like if you have 1 and again if you have seen 1, it will just override that 1 with 1 and it will do whatever operation that you are performing. Okay, that's it. And how to access the hash map elements? By using these keys. Okay, let's say this particular hash map is being under the variable of MP, then you can say MP of 2, then you will get a answer as 3. Okay, like this is a key basically, and if you do this something like this, you will get a value. So this is how hash map works. Now what is the requirement for an object to be used as a key or a value in the hash map? So we have discussed what is a key and what is a value, and they are saying that what is the requirement for an object to be used as a key or value. So now the key or value object that gets used in hash map must implement equals or hash code method. Now the hash code is used when inserting the key object into the map, and equals method is used when trying to retrieve a value from the map. So basically it's something like equals is used for finding an element, and a hash code operation is being used for inserting an element. Okay, that's it simply. How does a hash map handle collision in Java? So what is a collision? Okay, I will tell you that. So let's say in hash map you have 1, 2, 3. Now again I am trying to map this 1 to first I have mapped 1 like 10, 11 and 12 here. Now again I wanted to, for 1 I wanted to map 15. Now in that case this is going to be overridden, right? But I don't want like that. I wanted to be all the values to be handled over there. So in such cases, how to handle this? Okay, this is a collision, right? So we have already data, again we are trying to insert the data back again, so it will collide. So how to handle these things? So they are saying that so this is that in Java, this is how you will be importing the hash map. So in Java uses the approach of chaining the handle collisions. Okay, so we follow the chaining method. So in chaining, if the new values or with the same keys are attempted to be pushed, then these values are stored in a linked list stored in bucket of the key as a chain long with the existing value. Yes, so makes sense. So I will tell you with an example how this is works. Okay, let's say I have a values of 10, 11, 12, 11, 12 and 13, 14 and 15. Now I will be having one hash key as 2. Okay, hash key as 2. Now how does it work? So basically I will be mapping all these things with the mode of, let's say I will take this and 10 mod 2, which is an hash key here. So the value is 0. So I will map all the 0th remainder values to the 1 key and all the 1 remainder values to the 1 key. Let's say here I have a key values of 0 and 1, right? So if my hash key is 2, then I have these are the only 2 possible ways that I can get. Now so 10 mod 2 is 0, so I need to assign the 10 to the 0th key. So I will do that here. Done. Now I will take out the next guy, which is 11. So 11. So 11 mod 2 is going to be 1. So I need to map the 11 to the 1. Now I will get 12. So 12 mod 2 is going to be 0. So it means that I need to assign this 12 to the 0th key. So already, if you can observe, already there is a 10 which is been assigned to the 0. Now how can I assign 12? So here I will follow an linked list method. Okay, linked list. So starting with the node of for the key of 0, I will be having a linked list. Done. Now 13. So 13 is going to give me the remainder as 1. So which means that I need to give it to the 1th key. So already 11 is existing there. So I will form a chain here. I will form a chain. Okay. Now there is a 14. So if I divide, like the remainder is going to be 0. So it means that I need to map it here. And again, so you got it right. So I will, for the every key, if there is a collision is occurring, then we are forming an chain like structure. Okay, we are storing the data in the form of linked list. Okay, this is how we handle collision in the hash map or hash tables. In worst case scenario, it can happen that all keys might have the same hash code, which will result in the hash table turning into a linked list. So they are saying that let's say if I have given all the even numbers here, okay, like 10, 12, 14, 16, 18, 20, 22, like this, then all the values are going to be mapped to the 0 itself, right? 0 only, 0th key only. So that is what they are saying that. So in this case, a searching will be taking big O of n, right? Big O of n. So if I start from the, like if I wanted to search for 20, then first I will be starting from 10, then 12, then 14, 16, 17, 18. I will be searching in the max of n elements, right? So that is what they are saying, that in worst case, big O of n will be the complexity, as opposed to big O of one time due to the nature of linked list. Hence care has to be taken while selecting the hashing algorithm. So this is an you need to be very careful while telling if you have used an hash map in your data algorithm, and you should be very careful while telling the complexity over there, because in worst case you will be taking login time, and in best case it will take big O of n one time, which is a constant time. So please make sure that you won't get confused. Now what is the time complexity of basic operations get and put in hash map? So yeah, so they are saying that get and put operations. So basically these are the two operations that we perform on hash map. Okay, get is accessing, and put is for inserting. Okay, so they are asking us what will be the time complexity over there. So in best case, okay, if you are following and where you will be storing only one value to the each key, then in that case the both operations will be big O of one time, which is a constant time. But if you have if you are taking like where your map is in this particular form we have discussed earlier, the complexity is going to be, in worst case it is going to be big O of n. Okay, let's discuss another problem. So the next problem is, what is a priority key? We have talked about queue and stack, right? So what is this priority queue? So a priority queue is an abstract data type that is like a more a queue, normal queue, but has priority assigned to elements. So let's take one example, then I can tell you in a better manner. Okay, so let's say you are in a hospital, okay, and which follows the first come first serve, right? Like first in first out. Now you are all guys are in a queue and you went to hospital for a normal checkup, okay, consultants, okay, normal checkup. Now so you are standing in a queue and suddenly, all of a sudden, someone came up with an accident, okay, met with an accident. Now there is only one doctor, okay, who is whom you are going to check up for. So now what what is going to happen? He will stop the queue. Okay, he will stop the line here and he will directly jump to the accident paste. Why? Because he is the priority case, right? He is the one which has highest priority. We need to give them priority. So that is what a priority means. Okay, so here in our case of priority queue, everyone will be having some priority. Okay, everyone, let's say if we have taken politicians, okay, someone like MLA, MP, and governor, a CM and PM. So everyone has their own priority. Okay, if like MLA, until this PM comes, everyone is like CM is the top one, we need to give them priority, something like that. Okay, so here we will be maintaining two queues. So one to maintain our data and one to maintain our priorities. Okay, so this is what a priority queue means. So the one who is having a highest priority will be going first. Okay, one who is having lowest priority will be going out. So it can be vice versa as well. Like if your program wants to be like who is having a lowest priority, they need to go to the first. So it totally depends upon the application that we are using. Okay, now so elements with higher priorities are processed before the elements with a lower priority. That is what we have discussed. In order to implement this, a minimum of two queues are required, one for data and another one for priorities. So this is what. And another thing about a priority queue is, so we have a concept called heap data structure. Okay, which we will be talking about in a later part. Okay, so in heaps we have a max heap and min heap. So mostly to implement these things, we will be writing periodic queues. Okay, we will be using periodic queues. So we'll talk about what is heap and what are these max heap and min heap in the last question, which is an 40th question, I guess. Okay, we'll talk about that during that time. So just as of now, we can implement max heap and min heap with the periodic keys. That's it. Just keep that in mind. Now, can we store duplicate key in the hash map? So I guess we have answered this question earlier. So we can't store the duplicate values in the hash map. If we try to do that, it will override the values and keep only one copy. That's it. So this is what they are saying. No, okay, duplicates keys cannot be inserted into hash map. If you try to insert at any entry with an existing key, then the old value would be overridden. Okay, so old value would be overridden with the new value. Doing this will not change the size of the hash map, right? So we are just overriding. So size doesn't matter. So this is why the key set method returns all keys as a set in Java, since it doesn't allow duplicates. Now here comes the trees. Yeah. So tree data structure. What is a tree? So what is a tree? So tree is recursive non-linear data structure. As we talked about what is a linear and non-linear, so tree comes under the category of non-linear. Consisting of set of one or more data nodes, okay, where one node is designated as a root and remaining nodes are called as a children of a root. So basically, we again, just like linked list node, for tree as well, we will be having a node. Okay, node. So you can consider this as a node. And here every node will be having three parts. One is data, and this is a right node pointer, and this is left node pointer. Okay, so every node will be having these three pointers. They are saying that so for every tree we will be having one root. So root means the topmost element, the very first element that has been created in the tree, and all other, if we have one root node, then all other nodes will be called as an either children's, okay, or like subtree kind of things. Okay, so we'll talk about the terminologies and all in the later part. Now tree organizes the data in the form of hierarchy manner. So what is this hierarchy manner? So if you can see, like let's say I have a folder named a desktop. Okay, under the desktop I have two folders. One is a scalar, another one is personal. Okay, and again in this scalar folder I will be having few other folders. Let's say arrays, like where I will be storing all the programs related to the array topic, then linked list, then trees, and in personal I will be having, let's say, documents and pictures and videos. And again in trees I will be having different topics. If I say like a 2-pointer, okay, a sliding window technique, and queues or stacks kind of thing. And even in trees as well we will be having different types like binary trees, binary search trees, AVL trees, red black trees. Okay, so I will be storing something like this. So can you tell me now, this is going to look like as a tree, right? Okay, where we will be having one root that has a desktop. Under that desktop we will be having folders. So this is what hierarchy, right? So 1-2 layers. So on very first layer we will be having desktop, then scalar and personal folders, again folders, again programs kind of stuff. So this is what they are referring to as a hierarchy data structure. So the most commonly used data structure is a binary tree and its variants. So as I said, we will be having different trees, okay, different types of trees. Okay, I will name the few. Okay, binary trees, binary search trees, AVL trees, and complete binary tree, sorry. Okay, and B trees and red black trees. So these are also all called as a trees. Okay, but different types of trees. Among all these trees, binary trees and binary search trees are very, very important. Okay, and even binary trees are more important than binary search trees, if I wanted to put it in a name here. Okay, so if you are preparing or if you are aiming for big companies, big tech companies, or big product based companies, then you should need to solve at least 50 plus problems on binary trees. So that is going to be a good count and you can able to solve the any problems. And to learn binary trees or any trees, then the prerequisites would be recursion. Okay, recursion for sure, and some hashing. We use hashing in few tree problems. So yeah, even this is secondary. Okay, this is secondary. Like recursion is a must to learn the tree. So if you wanted to looking to learn tree topics and recursion, please, I have made a video on both trees and recursion where I will be solving few plenty good amount of problems starting from the basics. So you can watch it there as well. Now let's come to the applications of the trees. So first applications are file systems. We have seen this, right? So we have seen this application here. So this one application where we will be saying that this is how our file architecture is being stored. Okay, then comments on social media. So what is comments on social media? So if I say, let's say someone has posted a picture post and I have commented, and for my comment multiple people can comment it again. Yes, and for comment multiple people can comment it again, right? And can I say this is going to be tree structure? Yes. Okay, and family trees. So a family structure, so where we will be having starting from the grandparents, then parents, then generations, and then our next generations like children, and so their children. So this is going to be like tree structure. Okay, and if you want you can, like, they will be representing two things here. So let me open my, so we will be having a root. Okay, let me take this out. Okay, let me draw this here. Okay, so we will be having first root, a root. Okay, so under this we will be having different trees, right? So I will be writing binary tree here. So here it is an NRA tree, so where we will be having like different number of amount of childs to a particular root. Okay, now this is a root, and here this is called as edge. So what is the edge? So edge is being called as a connecting point to the one level to the another level. Okay, it creates a representation. Okay, it creates a connection between two nodes, and the data present in the node is called as a key. Done. Now these two, okay, like for this particular root, these two will be called as a siblings. Yeah, siblings. These two will be called as a siblings. So what is a siblings? So in general, in real world, we call one level. Okay, like if I say me and my sister, we call as a siblings, right? So we are belongs to one same generation. You can consider this as one generation. Okay, and then we have a parent. Okay, and we have parent. Let's say if I want a parent of, if I wanted to parent of these guys, I can say that for these two, this is the parent, right? And I can say that this is also another subtree. Okay, subtree. And the nodes which don't have any children, are called as a leaves. Okay, nodes which don't have childrens are called as leaves. Okay, the subtree means a part of a tree. A parent means which has some childrens, then that is called as a parent. An edge means connecting point between the two nodes. A key means data which is present inside a one particular node. And the root means the topmost element where a tree has been begun. A siblings means which belongs to the same generation, or which belongs to the same parent. Okay, which belongs to the same parent. So we have discussed enough, and now let's move on to the next question. So what are binary trees? Yeah, good question. What are binary trees? What is a binary? What is a binary? I can say that two, either 0 or 1. So when I say binary, it is 2, right? 1 or 0. So this is what a binary tree means. Okay, so for each parent or for each root node, we will be having two children, at most two children, at most. Okay, so let's say I have a root. Okay, let's say I have A, and for A we will be having two children, B and C. Okay, and for B again I have two children, for E and D. And for C I have only one children called F, and for F again I have two children. So let's say G, H. Okay, and for E I have another children called X. So here you can if I say for each node we will be having at most two children, then it is called a binary tree. Okay, so a node, okay, a tree which has, okay, at most two children for every node, then it is called as a binary tree. So you can consider these two diagrams as well. Okay, so where in the first, in left hand side we will be having a normal tree. Okay, where we will be having three nodes here, then again like for everything we will be having again 3. So which is not a binary tree, right? Which is not a binary tree. So if you consider this tree, so here we will have two nodes for this, and for this we will be having 2, for this 2, for this 2, and for this we will be having 0, 0, 0. So I said at most 2. So it can be 0, it can be 1, it can be 2. Okay, these are the 3 valid things accepted. So this is what a binary tree means. Now let's move on to the next question. So what is the maximum number of nodes in a binary tree of height k? What is a height? Okay, what is a height? So let's say a height is the number of levels it has. Okay, so from this it can be considered as a 1 height. It can be considered as a 1 height, 2, 3. Okay, like sorry, 3, 4. Okay, this is a height of 4. Okay, now their question is, there will be having a height k, and they are asking us to what is the maximum number of nodes that you can have for the height of k binary tree. So let's see Okay, first let's try to draw the tree which has the some minimum number. Okay, let's say, okay, so I have this, then 2, then 3, then I have this, sorry, 3, and sorry, 4, 5, this 6, 7. For this again I have 8, 9, 10, 11, 12, 13, 14 and 15. So this is the height of tree. Okay, 3. So here, okay, like so until here 1, 1 and 1. Okay, so the height is 3 here. Okay, the height is 3. So now tell me how many nodes are there. Can I say that 15 nodes? So here it belongs to the 8, it belongs to the 4, it belongs to and 1. So what is the one thing that you have identified? So by increasing the one level at each time, we will be going in a 2 power manner. 2 power manner. Okay, so for 3 size we will be having at max we will be having 15 nodes, which is going to be 2 power k plus 1. So here k is 3, right? So 2 power 3 plus 1 is going to be 4. So 2 power 4 is 16. So and minus 1. So this is the formula that we can get. Yes, so they are given something like that only. Now write a recursive, next question is write a recursive function to calculate the height of a binary tree. Okay, height of a binary tree. So let's take one binary tree here. 10, 2, 3, 4, 5, 6 and 7. So in this case the height is 3. Okay, the height is 3. So if I am currently standing at this particular node, so can I say that the maximum left subtree, the height of maximum left subtree and the height of maximum right subtree plus 1. So why plus 1? I need to include this particular node as well, right? So can I say that max of a left subtree, okay, sorry, a max of left subtree comma right subtree plus 1 as my answer? Yes, I can. So by using this formula, how can we write our code? So for this we need to know a traversal. We need to traverse through all the nodes of a tree. Yes, all the nodes. We need to traverse through all the nodes of a tree. So how can we traverse through all the nodes? So we have 3 things, okay, to traverse through all the nodes. So which is, we have 2 techniques. One is DFS and BFS. Okay, DFS means a depth first search. We will be first, let's say we have a tree something like this. So we will go till the depth wise, like we'll reach till the leaf node, and then we will go back and then we will come to the another way. Okay, which means we will come to the start from the root, come to the leaf, then again we'll go to the another way. Okay, but in BFS manner we will be going in the fashion of breadth wise. Okay, so 1 breadth, 2, so breadth means horizontally, DFS means vertically. Okay, so for this we have again under this DFS again we have 3 things: pre-order, post order and in order. Okay, pre-order, post order, in order, and we'll discuss about them in detail, okay, in later part. Now just try to solve this particular problem, then we'll see. Okay, so if I'm currently, let's say I have tree like this. Okay, now first I will give the pass the argument as my root node. Okay, which means I'm standing at here. Now what is the first thing that I need to check? So I need to check if that particular root node is null or not. If it is a null, what does it mean? I don't have any nodes. Okay, so I can simply return 0, right? So first thing, check if root equal to null. So if this is true, you can simply return a 0, right? If it is false, what does it mean? You need to go to the left subtree, then you need to go to the right subtree, and you need to check the maximum of them. Okay, you need to get the maximum out of the left subtree and right subtree. Okay, now let's say I will go here. First I will go to the left side. Okay, then I will calculate the height of this particular 2. Okay, again I will check. Okay, I will make a recursive call. Okay, you can see that here. Okay, I will be making a recursive call, and then I will check root is equal to null and no. So I will go to the left subtree now. Left subtree. Now again I can check root is null or not. So again I can see root is not null. So I will go to the left. Now is there anything here? No, there is nothing. So I will return 0. I will return 0 here. Okay, I am done going to the left side. Now I will go to the right side, and I feel that there is nothing here as well. Okay, there is nothing here as well. So the right subtree of 4 is going to return 0. Now you need to take the maximum of, for each node you need to take the maximum of left subtree, right subtree, and then you need to add the 1, which is a current level, right? So maximum of 0 and 0 is going to be 0, right? Now you need to add the 1. So 0 plus 1 is going to be 1. Okay, which is this. Okay, the left subtree of 2 is going to return 1. Okay, and then you will be going to the left side, right side of the 2, and again you will say that it will return 0, it will return 0, so you will return 1. So among 1 and 1 of 2, so left subtree of 2 is 1, right subtree of 2 is also 1. So if you take the maximum out of them, you will get 1, and you will add the current node, which is again 1. So 2. Okay, so I'm going to the left subtree of 1, you will get a height of 2. Done. So now let's go on to the right subtree. So I will go here, and I can see that there is the root is not null, so I will go to the left, and then again root not, so I will go to the left. So here I will say it will return 0 and return 0 because it don't have any left and right subtree. So I will return 1 here, right? 1. Now it will go to the right, which is a null. Okay, it will return 0. So among 1 and 0, which means a left subtree and right subtree, the 1 is the maximum one. So it will return 1 plus 1. So 2 here. Now for 3, it will go to the right, and there is nothing. So it will return 0. And out of 2 and 0, 2 is the maximum. So it will return 2 plus 1. So which is a 3. Done. Now for this, again you will return 2 plus 1, which is a 4. Done. So for this, the height would be the 4. Done. I hope you have understood. So this is how, like, if you wanted to write the code for this, you can check this out. This is how you will be writing the code. So write a code to count the number of nodes in a binary tree. So they are asking us to write the code to check the how many number of nodes present in the binary tree. Okay, let's say if I have given a binary tree like this. Okay, now how many nodes are present in this? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So at max I have 9 nodes. 9 nodes. So my answer would be 9 here. So can I say if I want the total number of nodes here, then can I say that the total number of nodes at the left hand side plus the total number of nodes right hand side is going to be my answer plus 1. Like so, count left side, okay, plus count right side plus 1, right? So whatever how many number of nodes are there in my left hand side, it is going to return 3, and how many number of nodes are there in my right hand subtree, it will return 5, and here I will do plus 1 for the current root nodes. I will do plus 1. So at max it is going to be 3 plus 6, it is totally 9. Done. Okay, so it is simple. Okay, you can try it on your own. So this is the code that you can check it out. So three traversals. Okay, as we have discussed, there will be three traversal techniques. Now let's try to understand three traversals. In this tutorial, we will be learning about trees right from the basic. So what are the contents that are going to cover in this entire tutorial is different types of trees available and binary trees, and what are the techniques to traversal in an particular tree, and also we are seeing the implementation of trees and implementation of traversal techniques. And coming to prerequisites, it will be good if you know what is a structure and a class. And to study trees, the recursion is must and should. Okay, so if you don't know what is recursion, please go and watch my previous video which is made on recursion. And yeah, that's pretty much. Okay, so let's get started. Oops, before starting we do have few formalities to do. So first one, if you are visiting channel for the first time, don't forget to subscribe. If you like the content, please hit that like button up, and if you have any queries, please let us know in the comment section. Now let's get started. Now let's get started with the introduction to the trees. So I can simply say that a tree is a non-linear data structure. What does it mean by non-linear? So basically, data structures has been classified into two types. One is a linear data structures, like a linear data structures like arrays, linked list, stacks, queues. Okay, and another types are a non-linear data structures. So non-linear data structures means trees, graphs. Why this is or called as an these are all called as an nonlinear data structures. Basically, a tree and graphs stores the data in the form of hierarchical. Okay, so what does it mean by hierarchical again? So let's see. So basically, if there is something here, okay, if there is something here, and data has been stored inside to that, like whatever it stores, it will be linked to that on top of that level. Okay, now again for this level, it might have something. Okay, so it might be anything. Okay, it can have n number of things. Okay, so can I say that these are all one level, these are all one level? Can I say that? So these are all in one hierarchy. So here one hierarchy, then hierarchy, it has something, it has something, it has something, right? So this is how that tree stores the data. Okay, now by this means we are calling it as a hierarchical data structure. Now let's see, there are a few things that we need to know before starting the actual tree representation or coding, whatever it might be. Okay, so first one, a root. Okay, so I will take a simple tree. Okay, now then I will explain everything on that tree itself. Okay, so let's assume we have a tree something like this. Okay, now let's see, so what is a root? So a root can be defined something like this. So root will be the starting point of the tree. Okay, so here where did that root has been started, sorry, tree has been started here, right? So is there anything on top of a? No, there is nothing in top of a. Is there anything below the a? Yes, everything, whatever the comes, whatever the data comes, that will be below the a. So can I say that a will be my top? So by that means I am calling it as a root. Okay, now something parent. Now the next one is parent. What does this mean by parent? What does this mean by parent? So a parent is a node. Okay, so which has some childs. Okay, let's see. So I can say that a has this B and a C. Okay, so from A there are two things are coming. Okay, so they are called as an childs. Okay, childs. So these B and C are childs of A. Okay, so now these are all the childs who will be called as a parent. A, right? So it's a parent A, and childs are B, C and B of childs of A. Cool. Root is A. Now, what are all the other parents that you can see on this particular diagram? So here, can I say that B is a parent of D and E, right? So B is also a parent. So can I say that G and H are childs of C? Yes. Okay. Now is there anything below this D? Nothing. So I can say that D is not a parent. Okay. So that is what happens. Now the next one is, so basically each so I forgot to say, everything will be called as an one node. Okay. So this will be called as one node. This will be called as a node. Okay. This will be called as a node. Now a degree of a node. What is a degree of a node? A degree of a node means the outgoing nodes, number of outgoing nodes from that particular node. Let's say from C, how many nodes are going, like how many childs, let's say childs. Okay, so how many childs are there for C? There are two childs, right? This is G, this is A, H. So there are two childs. For A, how many childs are there? Again two. Okay, now tell me, if I add one thing to G, something X. Okay, now tell me what is the degree of a G? It's a 1. Right, hope you got it right. So I can say that a degree is something, the number of children it has. Okay, particular node has. Now parent done, root done, child done, degree done, and center. So and center, what is this mean by and center? So and center is something like this. Okay, so let me draw another tree. Okay, so okay, now can I say that for this particular node, this is an center? So the top, okay, the previous one where it has been generated. Okay, now can I say that this is a ancestor of this particular node? Yes. So let me tell you one simple trick. Okay, so this will be your current generation. Okay, so this will be called as a parent, grandparent, grandparent, right? So these are all the ancestors of this particular guy. Okay, now what are the ancestors of this guy? Who are the ancestors of this guy? This one, this one. Okay, so who are the ancestors of this guy? No one, because a root itself is the starting point. Okay, so there will be no ancestors for the root. Okay, now if there is an ancestors, then there will be a descendants as well. So who are called as descendants? Okay, the one which it has like the childs of that particular node. Okay, let's see. Okay, let's see. So this is one thing. Okay, now if I wanted to say who are the descendants of that particular node, I can say that this guy and this guy. I can say that, right? These are all. Now you can simply call as an, so consider this as your parents. Okay, parent. Okay, now you might be having, like, he might have one daughter, one son, something like that, right? So you can relate to that particular thing as well. And the next one will be siblings of a node. Let's say what are all the siblings. Okay, so the siblings means which comes from a same parent. Okay, the nodes which comes from same parent. Let's say I have a tree, something like this. Now for these two guys, who is the parent? The same one, this one. Now can I say that these two nodes have came from same parent? So by that means this particular node will be an sibling of this guy. Okay, again it will be a vice versa as well. So for this guy, who is a sibling, he might, right? So let's suppose he has another node, okay, another child. Then for this particular node there are two siblings. Okay, two siblings. So this is how things works. And the next one is a leaf node. Leaf node. Leaf node. What does it mean by leaf node? A node which don't have any outgoing nodes. Okay, a node which doesn't have any children's, okay, child nodes, then we are calling it as a leaf node. Okay, so here if you consider this particular node has no childs, this particular node has no change, this particular node has no childs, and this guy has one node, this guy has one node, this guy has one node, this guy has two nodes, this guy has one node again, right? So this is the, okay, so a last level of a particular node, okay, will be called as a leaf nodes. Okay, and again internal node. Okay, a internal can be defined as a node which has at least one node, one outgoing node, or one parent, oh sorry, one children, is called as an internal node. Okay, a node which has at least one children is called internal node. Okay, now let's see. Now there is another important term, height and depth of a tree. Okay, height and depth of a tree. So in basic, okay, so height can be defined as an the max path from root to leaf node. Let's say I have a tree something like this. Okay, I have something like this. Okay, now tell me what is the highest path from starting from a root to leaf node. Okay, now this guy, this guy, this guy. So here I have path which is very highest. Okay, it has a 4 nodes. Okay, 4 nodes path. So if I consider this path, it is only 3, it is only 3, right? So here we have a 4 nodes, 4 nodes. So by means that we can say that number of nodes in a path minus 1, so then that will be your height. Okay, so here since we have 4 nodes involved in that particular path, it's a n minus 1. Okay, 4 nodes minus 1, it's a 3. Okay, I can say that the height of this particular tree is an 3. Okay, now what will be the depth? Okay, now let's say what is the depth. Okay, you have a tree like this. Now if I wanted to find, if I wanted to find depth of this guy, okay, depth of this guy, I can say that from root, okay, starting from the root, what is the number of nodes involved in that particular till that particular node. So there were only one node which is a root, right? You can exclude this guy. Okay, so now I can say that a depth from this particular from starting from root to this particular node is a 1. Now at the same time, if you want to find this guy, what will be the depth of this guy? It will be 2 now. It will be 2. So why? Because starting from the root till that particular node, there are 2 nodes involved. Okay, you can simply call it a path as well. So 1 guy and 2 guy. Okay, so you can consider that as well. Okay, so that will be defined as a depth. Cool. Let's discuss about a binary tree. So binary tree is a very important tree which is being asked in many interviews. Okay, so you can expect a lot of tree questions from binary tree and binary search trees. Okay, we'll talk about binary search tree later. Now we'll discuss about what is a binary tree. So a binary tree is a node or every node. Okay, let's call every node in a tree must have at max of 2 children. Okay, to a node. So I'm saying that let's say you have a node. Okay, it must have either 0 or 1 or 2 children of the only. Okay, let's say so we have a node and for this particular node we have 2 children. This is valid. Okay, we can have 0 or 1 or 2. Okay, at max 2 children. Okay, now we have a 2, it's valid. Now for this particular node, again we are having 1 node. Yes, again it's valid. Now for this we have a 2 child nodes, it is also valid. Now for this particular node we don't have any child nodes, so the degree of that particular thing will be 0, it is also valid. Okay, you can consider these things as a degree as well. Degree of every node should be less than 2, less than or equal to 2. Okay, now then we can say that it is a binary tree. Now again in binary tree we have a couple of types. The first one is full binary tree, full binary tree, or it can be called as a proper binary tree and strict binary tree as well. Okay, a proper binary tree and a strict binary tree as well. And then next one will be complete binary tree. Okay, then the next one will be a perfect binary tree, then a degenerate binary tree, at last it's a balanced binary tree. Okay, Now we'll talk about each one of them. Okay, so full binary tree means, so a tree which has either a 0 or a 2 nodes or 2 childrens, then it will be called as a full binary tree. Let's say, unlike a binary tree, for binary tree, what are all the possible child nodes? 0, 1 and 2. Okay, so in this particular full binary tree, we can say that 1 is not allowed. Okay, so 0. Okay, so root, and for this we have 2, and for this again 2, and for this particular node we don't have any child nodes. It is a full binary tree. Okay, we have only either 2 or a 0 possibilities. Okay, now let's say if I say, just tell me, is this a full binary tree? And no, this is not a full binary tree, just because of that fact that for this particular guy, for this particular node, we have only one node, one child node. So 1 is not allowed. Okay, it has to be either 0 or 2. Okay, in that, by that means we can say that it's a full binary tree. Now we'll see what is a complete binary tree. A complete, there are certain rules to follow. Okay, so first rule is all the nodes are completely filled except the last level. Okay, let's see. So if I have a tree something like this, okay, so before coming to this particular level, we need to first fill this level. Okay, so let's say, so here we missed out entering into this particular right of that particular node. We have just going in a left manner, right? So this is not allowed. Okay, so before coming into this particular level, you have to finish this level. Okay, so let's say first I have to fill the root, then I have to enter the left. Okay, then I have to enter the right. Okay, so now it's completed, because binary tree has only at most two things, two child nodes. And now I need to start from the left. Okay, left. So for this guy here and this, and now let's say I can't enter like this. Okay, I can't enter like this, just because I need to first, before coming to right side, I need to first complete the left side of that particular node. So I have to complete this, then only I have to come like this. Okay, now this is how a complete binary tree looks like. Okay, now the second point is, in last level all nodes must be as left as possible. Okay, let's say we have another level. Okay, so I have stopped here. Okay, there are nothing to enter in a tree. Okay, nothing to push in a tree. Now, so where I'm ending at, so I'm ending at leftmost side of that particular tree. I can say that, right? Now that is what this second definition is. Now third rule, so the node should be added from the left. So as I said earlier, we need to start from the left side of the each level. Okay, so this one is one level, this is one level, this is one level, this is one level. Okay, now for every time we are starting fresh, a new line, fresh level, we need to start from the left side. Okay, now that is a complete binary tree. Now let's see a perfect binary tree. So now perfect binary tree can be defined like all the leaf nodes of particular tree should be in a same level. Okay, same level. Let's say we have a tree like this. Now tell me, what are all the leaves here? This one is a leaf, this one is a leaf, this one is a leaf. Now all the leaves are in a one level? No. Okay, so this is one level, this is one level, this is one level. So one leaf is in second level and all other leaves are in third level. So this is not a perfect binary tree. So how does that perfect binary tree looks like? So like this. So here all the leaves. Okay, so this one is a leaf, this one is a leaf, this one is a leaf. Okay, there is no another leaf. So all these leaves are in same level. So this is called as a perfect binary tree. Now the next one is degenerated tree. Okay, degenerated binary tree. So basically it's very simple. Okay, so it looks like this. Okay, it keeps on going at one end only. Okay, so there is something like this as well. It is going in a one side. Okay, so let's say I have started from a root. Okay, and then I move to right, then again 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 move to right. Now there is another possibility. I have started from the root, I have moved left, then I have moved left, then again I have moved left, again I have moved left. So I'm going starting from the root and going in a left manner. Otherwise I'm starting from a root and going in a right manner. That's it. Okay. So that is called degenerated. Let's see how to implement an binary tree in program. Okay. So in this particular thing, I will be discussing the code of binary tree in both languages like C++ and Java. Okay, let's see. So a general binary tree something looks like this: 2 and 3 and 4, and this will again have 5 and 10 and 11. Okay, let's assume. So let's try to implement this particular binary tree in an program. Okay, so I can say that this is one node. Okay, so this is one node, one node, one node, one node, one node. So everything is a node. Yeah. So and what every particular node has, like every node has some data, and this particular node is pointing to something. Okay, and this particular node is pointing to something. So can I say that it is pointing to things? One is a left, one is a right. Yes. Now let's see how this particular thing will be represented. So 2, it will have something like this. Okay, now this a left. Okay, so left thing will be pointing to again 3, so again which is a node. Okay, so again 3 left is pointing to something called 4. Again a 3 right is pointing to node 5, and right to the 2 is a 10, again which is a node. Again right to the 10 is 11. So here the things that you need to observe here is every node has something like data and a left pointer and a right pointer. Okay, now let's discuss about C++ code. So how will you represent the same in C++? Okay, there is much difference between both C++ and Java code. Okay, it's only syntactical changes. Let's see. So in C++, we will be using a struct to define a node. Okay, so what it contains, a particular node contains some data that is in the int format, and again we have some both a left and right pointer. Can I say that again a left and a right pointers are nodes, right? Again, then what will be the type of these things? Again struct node star left, struct node star right. Good. Yes. Now let's see how will you implement the same in Java. Okay, so in Java you don't have any struct. Okay, so you have to use a class. Okay, a class node. Okay, so you will have int data. Okay, then here the type of a particular left and right are node, node left, node right. Now, so how to assign a data? Okay, so we have a concept called a constructor. We use that concept to initialize the values to an node. Okay, so how it looks like. So here a constructor name should be equal to either a struct name. Okay, so here the struct name is node and here the class name is a node. Okay, so constructor name should be equal to that. So int value. Okay, so since we will be having some value, like so while creating a particular node we have to pass that value to that particular given node. Okay, now so we need to assign that value to data equal to val. Now what will be our left and right? Okay, so just assume so you are creating a node. Okay, so since you are just creating a node of root, you don't have any kind of left and right, so you have to initialize them to the null. Okay, so left right equal to null. Okay, the same code goes in Java as well. A node into value, so here you will be assigning this dot data equal to val, and both a left and the right equal to null. Okay, in case of Java your null should be capital. Okay, Here, done. Now you have created an like definition for how to define an tree node. Now how to assign a values to this. Let's see. So we'll have a main class, main. So first you need to create an root of a tree. So struct node star root equal to new node. What is the data of our node? So like a root node, it's a 2. Okay, so you will pass 2 here. Done. So it will create an something like this. Done. Now so you need to create an left and right to that particular things now. So how will you do that? So root left equal to, so now you are pointing to here. Okay, so root left. So again it will be a new node of, let's say 3. Okay, so you have created a 3. Done. So now you will be creating a left to the left. Okay, so root left 3 left 4. Okay, so you have to create something like this. Then how will you do that? Root left equal to new node of 4. Done. Now I wanted to create an right to this guy, right to this 3 node. Okay, so what will be the path? So root left and root left right. Okay, so root left right equal to new node of 5. Done. Now I wanted to create an root right. Okay, so I wanted to create something like this, a root right of 7. Okay, so how can I create root right equal to new node of 7? That's it. Okay, so this will form an tree something like this. Okay, so done. So there is not much difference between C#, C++ and Java code. So here instead of using these things, you will simply use a node, and instead of these pointer symbols you will use dot. Okay, so that's it. So you can try on your own as well. So now let's see the traversal techniques of an tree. So what is a traversal? So basically in arrays and linked list, right from the 0th index you will be going to the nth index. So how you are using that, how you are going that? So by using for loop, right? So you will be initializing int I is equal to 0 and I less than n and I plus plus. So something like that. So we need something similar, okay, to traverse in a tree as well. So what are they? Okay, so we call them as a traversal techniques. So we have two things. One is a BFS, breadth first search, and a DFS, a depth first search. Okay, so we'll see. Okay, well, we'll take one example, and we'll try to apply these techniques on this tree. Okay, so let's assume we have a tree like this. Okay, so 1 and 1 to be right, 3, 4, 5, 6 and 8. Now let's say, so first we'll see the BFS. So BFS, what is a BFS? So breadth first. So breadth, right? So I can say that this is one thing, breadth, this, then this, then this. So similarly, can I say that we are going level by level? So first we are printing first level, then we are visiting next level, which includes a 3, 2 and 3, then these values of 4, 5 and 7, and then this last level 8. So simple, right? So breadth first means, so we are going a level by level. So we are printing level by, first we will completing the first level, and then we are going to second level, and we are seeing all the visiting all the values nodes in an particular level, then we are going to the next level, then we are going to the next level. So this is the breadth first search. Now we'll talk about the depth first search. Okay, so which is a very important, very important. Okay, so again in this particular DFS we do have 3 types. So pre-order, in order, post order, very important. Okay, so you can do wonders in trees by using these 3 things. Okay, so you can solve many problems. I can say that without these things you can't solve most of the things, okay, most of the problems in entries. Okay, let's see one by one. So before going into finding and how to traverse by using these things, now you have to remember a few things. One is for pre-order, okay, so in one particular node, what are all the things we do have? A data, left and right. Okay, so every node has these things. Now but with these things we are using like we are traversing through the entire tree. Okay, let's say in pre-order, first we are printing the root. So when I say root, it is the data, root data. Okay, now then left, we are moving to the left. Okay, left, then we are moving to the right. Okay, so first we'll do the whatever the data it has, we'll visit that particular data, then we'll go to the left. Okay, then we'll go to the right of that particular tree, okay, particular node. Okay, so now what is about in order? Okay, so it's a first we'll move to left, then we'll move to root, then we'll move to a right. Okay, so in post order, first we'll move to a left, then we'll move to right, then we'll move to a root. So now we'll take one example tree and we'll try to traverse, we'll try to use these 3 DFS techniques on that. Okay, so let's assume we have a tree something like this: 2, 3, 5, 6, 7, 8, 10 and 12. Okay, so let's take, so first we'll start with pre-order. What is a pre-order? Okay, so pre-order, what are the rules, what are the formula for pre-order? So it's a root data and left and right. Okay, now where do we start from? We start from this particular root. Okay, so what is the formula? RLR. So here it's an root data. Okay, root, and this R is right. Okay, so what is the first thing that we have? It's a root data. So whenever we have seen a root data, we have to get that particular node data to the output board. Okay, so here in this case, here we have 2. Okay, so we'll print 2 here. So by means that we have done with this particular R. Now what is the thing next thing? It's a L. So it means that it is stating that go to left side. Okay, we'll move here. Now again we'll repeat the same task for this as well. So first thing, root data. So we have 3. Now it is stating that go to left. Okay, by going left we will come here. Now RLR. So now again it is stating that root data. So we will have 6. Done. Now again it is stating that go to left. Is there anything to the left? It's a null. There is nothing. Okay, done with this L as well. Okay, so since it's a null, we are not going there. Okay, now go to left, right. So is there anything to the right of the 6? No. So we are not going to the right as well. So we are cancelling. So done with that thing. I can say that we are done with 6. Okay, now we'll go to the top, whoever called this particular 6. Okay, it's a 3. So we are done with this L. We have moved to L and performed all the operations, right? Now we have to go to right side of 3. So it's a 7. Now again we need to repeat the same task for 7 as well. It's a R. So it is stating that print the root data. Now go to left. Is there anything to the left? Is there anything to the left? No. Is there anything to the right? No. Right. Is there anything to the left? No. Is there anything to the right? No. So we'll cancel that thing as well. And then we'll go to the top, whoever called this particular thing. So we have visited the right as well. So we'll cancel that. Okay, now again from here we will go to top. So you have done this operation, you have done this, you have moved to right, left as well. Now you have to go to a right side. So you will come here. So again you need to repeat the same task. So first R. So R means visit the data. So it's a 5. Now again it's a left. So you will go here. What is a left? Okay, it's a, again you will simply repeat the things. So again you have 8. Then it is saying that go left side. There is nothing left. Okay, now is there anything onto the right? No. So we are cancelling and we are going to the top. Okay, now currently you are here, you are done with, you have moved to left. Now you have to move to right. Okay, so right is 10. So RLR. Okay, now again first is data. So we will print that 10. Now it's a L, so L means go left. Is there anything to the left? Yes, there is 12, right? So you will move here and you will have LRL. Okay, now again first is our data, so you will print 12. Then again it is saying that left, go left, so there is nothing left. Again it is saying that going go right, there is nothing on to the right of the 12. So by means that we have completed this particular node as well. Now we'll go to top, whoever call this. Now we are done with L. Now we left with this R. So is there anything to the right to that particular 10? No. So we have completed that, and we have completed this node as well, and we'll go to the top. Okay, so we have completed the R as well. Okay, these are all the R, right? Now we'll go to the top. We have completed, and we have completed the R. So now check. So we have nothing to visit. We have done with all. Now check whether we have visited all the nodes of a tree or not. Okay, so first thing 2, then 3, then 6, then 7, then 5, then 8, then 12, 10. So done. We have visited the all the nodes on a tree. So this is how a pre-order works. Now let's see the in order. Okay, in order. So became little mess. Okay, let me draw the tree again. Now we'll try to see the in order traversal of this particular tree. Okay, so what are the in order traversal rules? First you have to go to left, then you have to move to root data, then you have to move to right. Okay, so let's write these things L R R. Okay, second thing is a root. Okay, now first it is saying that go to left. Okay, go to left. Now again you will have LRR. So again it is stating that go to left. Again you will have LRR. Now is there anything to the left of 6? No. So it means that we are done with left. Now what is the next thing? It's a root data. So whenever you have seen root data, you have to print that output, like whatever the node value, you have to print that in the output board. So here it's a 6. Okay, so by means that we have completed the R. Now it is saying that go to a right. Is there anything to the right? No. Okay, so we have completed this, and we'll go to the top. Okay, now we are done with left. Now what is the next thing? It is saying that print the data of the particular node. So here the node data is 4. Okay, we are done with this R. Now it is stating that go to right. Okay, so we'll come here. Now we'll again have the LLR. Okay, now first thing it is saying that go left. Is there anything left? No. Now the second R is a root, right? Root data. So we have to print the 7. Now it is stating that go to right. Is there anything right to the 7? No. Done. We'll cancel this. Then you will go to top. So you are done with second R. Then you have done with third R as well. So you have visited, you have traversed the entire subtree of this left side. Now we will go to the top. Now we are done with this R, LL, sorry. Now we will try to see this R. So here a root data. So whenever you have seen root data, you have to print that particular node data. So it's a 2. Now we are done with the second R. Now we have to go to the right side. Now you have to repeat the same task, LRR. So it is saying that go to left first. Okay, so you will come here. Okay, now it is same. Is there anything to the left? No. And next one is our root data. So what is the data here? 10. So we will print 10 here. So is there anything to the right? No. So completed. Go to the top. Call this particular thing. Now you are done with the left. Then what is the second thing? You have to print the data. So it's a 5. Now it is saying that go a right side. Okay, we will come here. So it's a 12. Okay, sorry, LRR. Okay, now you will say go left again. So is there anything to the left of 12? Yes, it's a 13. Okay, you will come here. Now it's a, is there anything to the left? No. Then it is a print. It is saying that print a root data. So we'll print 13. Then it is saying that go right. Is there anything to the right? No. So since you are done with this, then you will go here. So we are done with the left, and what is the next? You have to print the root data. So it's a 12. Now it is saying that go right. Is there anything to the right of 12? No, there is nothing to the right of 12. So we have visited this as well, and you will go to here 5. Now you are done with L, you are done with R, you are done with this R. You have moved to right as well. So I've done this. Done. So did we covered all the nodes? So 6, 4, 7. So let's count 8. Okay, so 8. Yes, we have covered the all the visited. We have visited all the nodes in a tree. Now, what is the last order? So it's a post order. Now again we'll take another example and we'll see. So it's a 2, 3, 5, 4, 7, 6, 8 and 10. Okay. Now we'll try to find the post order traversal of this particular tree. So what is a post order travel? It's first go left, then go right, then go root data. Okay. So L R R. Okay. So here R means this second thing is a right. So last we are having a root data. So make sure you don't confuse. Okay. Okay. Let's start. So first it is saying that go left. Okay. So we'll come here. Again we'll say RR. Then we'll go again. It is saying that go left. LRR. Now again it is saying that go left. Is there anything left of 4? No. Now it is saying that go right. Is there anything to the right of 4? No. Then it is saying that root data. So we have to print the data here. So it's a 4 first. Now you are done with this. Then you will go here. Okay, so you are done with left. Now you have to go to a right. Okay, so here right means 7. So here. So is there anything to left of 7? No. Is there anything right of the 7? No. The last one is a root data. So it's a 7. Now you are done with this. Then you will go here. Now you are done with this right as well. Now you have a root data. So it's a 3. Now you will go to the top. You are done with this 3. Now you are done with this left. Now you have to go to the right side. Okay. Now it is saying that go left again. So you will come here. Now is there anything to left of 6? No. Is there anything right of 6? No. Is there any, is that? So you have to print the data. So it's a 6. You have done with this node. Then you will go here. So it's a 5. So you are done with the left. Now you have to go to the right side. So first thing you will come here and it is saying that go left. Okay. Go left. So it's a 10. Okay. So is there anything to the left of 10? No. Is there anything to the right of the 10? No. It is saying that print the no. So it's a 10. Done. Now you will come here. Okay. So it is saying that go left. So done left. So it is saying that go right now. So is there anything to the right of the 8? No. Okay. Now it is saying that print the root data. So what is the root data? 8. Now done with this. I will go here. Now we have moved to left. We have moved to right. Now we have to print the data of node. It's a 5. Now done with this. Now we'll go here. We have moved to right as well. Now it's a root data. So it's a 2. So how many nodes are there? Totally 8. So we got 8. So this is how we'll travels these things in a tree. Okay. So again I am saying that these are all very important. So if you don't understand, please make sure that take another example tree, try it on your own. Okay, try it on your own. Solve take 2 to 3 examples and try to write the in order, pre-order, post-order traversals of that particular tree. Okay. Now we'll see the code of this, how like implementation details of this particular traversals. Now let's see how to implement and add these tree travels in C++. Okay, in C++. So there is no big difference between a C++ and Java code. Okay, so if you could have understood C++ logic, then you can easily implement Java logic if you know recursion. Okay, so let's see. First we'll start with pre-order. What are all the rules of pre-order? So first we move to first root, then left, then right. So this is the pre-order traversal. So let's say, now tell me one thing, tell me. So this is the root. Okay, so we need to start from here. So I will have a function like this, void pre-order, where I will be taking a node star a root. Okay, root. Now tell me, so let's assume if that particular given node is null. Okay, if that given root is null, what do you need to do? You need to simply return nothing to return. Okay, so like you won't have anything. Okay, let's say if root equal to null, you will simply just statement like a return. Okay, you are not returning anything, that's simply return. That's it. Now, if that is not the case, if root is not null, what you are going to do? So first thing, you will print the root data in your output. So cout a root data. Okay, root data. Okay, root data. Now tell me, so we are done with this part. Now what you need to do? You need to go to a left subtree, right? A left subtree. So let's go there. So again, tell me, after going to the left subtree, what you need to do? You need to do the same task what you did for root, right? So I can call a pre-order of root of left. Now my root will become a 3. Okay, now my root will become a 3. Now again I will check with whether root is null or not. So if it is null, I will simply return. That's it. If it is not null, I will print a 2, then 3. Then I will go to the left of 3. So I will come here. Now again I will do the same task. Again I will do the same task. First I will print the 5. Then I will go to the top. I will check. Now I will go to the left of this 5. Now left of 5 is null. So here my root is currently null. So I will simply just return from that. Okay, so if I return, I will come here. Now what is the statement? So after returning to the 5, so here we are done with the root, we are done with the L. Now we have to do with go to right, pre-order of root to right. That's it. Now again, after going into right side, I will find that again my root is null. So I will simply return from there. Okay, so I'm done with this. Now I will go here. I'm done with left of this. Now I have to go to right of this. Now again I will do the check for root equal null. No, it's not null. So I will go come here. So I will print a root data. So root data is 6. Now I will come to this second line here. Now I can say that go to a left. Okay, so after going to the left, it says that it's a root is null now. Okay, so you will come to here. Now I am saying that go to a right, right, go to right. So again the root is null, there is nothing to do. Now you will come back to previous node, you will come back to who call. That's how you will get to here 3, right? So after coming to 3, you are done with everything, right? So you have visited R, you have visited L, then you have visited right as well. So done. So you will go to here. Now you are done with R done, L done. You have to go to R side. So right side. So you will come here. Now RL. So again root. So it's a 4. Okay, you will print 4. Then you will move to left side. Again you will print the 4, 7. Okay, then you will move to left. You find out that there is nothing left on the left of the 7. So go and then you visit the right side of the 7. There is nothing. Then you are done. You will come here. So you are done with the left. So you will move to 8, right. So you will go print 8. Then you say nothing. You will go to 4. Then you will go to 2. Done. So this is how pre-order code looks like. Now let's go simply. We can quickly write the code for in order. So only one change, right? Only one change. What is that change? What is that change? So if root equal to null, what we will do? We'll simply return from there. If not, first we need to move to in order. LRR. So this is a root. So we need to first move to left of the root. So root a left. Okay, now what you need to do? Now you need to print the data after moving to which a root data. Okay, now after doing this you will move to right side. So in order root right, that's it, right? That's it. Now the one which is left is void post order. Again you will have a node star root. If that root is null, if root equal to null, you will simply return. If not, in all other cases, you will move to left side. So post order root left. Then after moving to the left, you will move to next right. So post order root right. After moving to the right, at last you will print the root data. Root data. Done. So let's discuss another question. Question number 29. So the question number 29 is binary search tree. What is this binary search tree? So it is also a binary tree. It is also a binary tree for sure, and but it will have few conditions. Okay, it is a binary tree, but it will have few conditions. What are the conditions? So if we have a root like this, okay, and all the right, okay, all the right side to the root elements must be greater than root data, and all the left side must be less than a root data, right? So this is the condition, and which is also a binary tree. So we know what is a binary tree. So a binary tree is a tree which we can have at most we can have two childrens. Okay, so valid is 0. We can have 0 children, we can have 1 children, and we can have 2 children. So at max 2. And what is a binary tree? Binary search tree. So binary search tree is a combination of binary tree with some conditions. Okay, so what are the conditions? So if we have a root and all the left side nodes of a root must be less than the root data, and all the right side nodes of a root must be greater than the root data. Okay, and if it has followed that condition, then we can say that it is a binary search tree. Now let's try to implement one binary search tree. So let's say we have given this data 1 5 7 3 let's make it 10 here, not 1, and 12 and 13 and 4 and 18. Okay, we have given this particular array. Then we need to try to write a binary search tree for this particular array. Now first element is 10. So first at max we will check if the root is null or not. Yes, a root is null. So whatever data we get as a first, we will be keeping that as a root. Done. Then we will move on to the next guy, so which is a 5. So now what is a 5? So 5 is so I will check first whether root is null or not. So here root is not null. We have 10 here. Now and then I will check the condition. So whether this 5 is less than the root node or root data or greater than the root data. So I found that 5 is a less than the root data. So I will keep that as a my left node. Done. Now let's assume I have 17. Okay, now I have 17. So a root is not null. Okay, now what I will do, I will check whether which is greater than or less than. So I find that 17 is a greater than 10. So I will say 17 to the right side. Okay, now I will go to the 3. So root is not null, and I will go to the left side again, which is 3 is less than right. So I will go to the left side again. I can see that left to the 10 is also not null. So I will say again, I will check left to the 5, right? Left to the 5. So which is a empty. Now I will say put it here. Now I will go to 12. So root is not null. Then I will 12 is greater than. So I will come to the right side, and then I can find that right side is also not null. So I will check whether 12 is less than or greater than the 17. So I find that 12 is less than 17. So we'll keep this at the left side. Now the 13. What is a 13? So I will check from the root, not null. Okay, so 13 is greater than 10. So I have to come to the right side. So I found that right side is also not empty. Then I will say check whether 13 is less than or greater than 17. So which is an less than. So it has to come to the left side. So again at the left hand side, which is also not empty. Now again I need to check whether 13 is greater than 12 or less than 12. I found that which is a greater than 12. So I will go to the right hand side, which is a empty. So I will put it here. Now I have 4. Now I have 4. So 10, it has to come to the left side of the 10. So which is not empty here. Again I have 5. So 4 is less than 5, so I have to come to the 3 now again, which is not empty. So now I will compare with 3. So I can see that 4 is greater than 3, so 4. Now I have 18, so I will start here. Root is not empty, root right is not empty, root so then I can find that 18 is greater than 17, so I will come to the right, which is an empty. Done. So this is how you construct an binary search tree. Now if you can observe all the left subtree or values are less than root, and all the right subtree values are greater than a root. And if you can pick up any parent, you can see this particular formula. So for 17, the left side we will have 12, which is less than 17, and right side we have 18, which is greater than 17. So this is the thing that we need to follow. Okay, this is called a binary search tree. Now let's move on to the next question. Now what is a AVL tree? So AVL tree is also a binary tree, but which follows an height balanced binary tree. What is this height balanced? So basically we will be having height, right? Let's say I have a node like this. Okay, I have tree like this. Okay, and here it is saying that height balanced. So for every node to its left and right subtree, height should be, okay, if you subtract, then let's say, let me write, okay, current balance equal to height of left subtree minus height of a right subtree must be equal to the either of -1, 0, +1. Okay, so if this current balance equal to any of these three, -1, 0 or +1, then it is an AVL tree. If not, then this is not a AVL tree. Okay, we should convert that as a AVL tree by swapping the nodes. Okay, so this is what an AVL tree is. Okay, so AVL trees are height balanced BSTs. AVL tree checks the height of a left and right subtrees and assumes the difference is not more than 1. Okay, the difference is called balance factor and is calculated as a height of left subtree minus height of right subtree. Done. Now we have a print left view of binary trees. Let's see the question number 30 first. So print left view of any binary trees. Okay, so you will be given in a binary tree. Okay, you need to print the left view. What is a left view? Okay, let's say if you are given this particular tree and you are standing here. Okay, you are standing here. Now what are all the nodes that you can see here from here? So this is the node which you can see, this is the node, and this is the node which you can see. So so now what are all the nodes that you can see? You can say that 4, 2, 1, 9, right? So this is called left view. And if they were asked you to find the right view, then what could be your answer? 4, 6, 7 and 9. 4, 6, 7, 9 for right. For left, this is the answer. So if you observe, can I say that, let's consider this as one level, one level, one level, one level. Can I say that in each level, you need to print the very first element, the very first node that you can visit. So here for this particular level, your answer would be 4. For this particular level, your answer should be 2. For this particular level, your answer should be 1, then 9. Is this what my left view? Yes. So if I print the last node, okay, if I print the last node in each of my level, then it could be my right view. Yes, can I turn this particular question to like that as well? So now how to write a logic to print all the left view nodes of an binary tree. Okay, so please pause the video for a while. Okay, think of it. Now we'll see one approach. Okay, where can we can do something like that. So we have studied about map, right? Hash map. So in this particular hash map, we can store all the nodes. Okay, let's say I will call this as a one level. Okay, so for zero, this is an zero level, this is an first level, this is a second level, and this is a third level. Right now, so for each level, if I'm visiting the level for the first time, okay, if I'm visiting level for the first time, and whatever a node that I am getting, can I say I can put that in my map? So let me do some dry run here. Okay, so let's pick up the tree. So 4, 2, 6, and 1 and 3. Here it's a 5, and here it's a 7, and it's a 9. Now let's say currently my level, while passing, I will pass this root node and I will pass my level as a 0. And let's put some map here. Okay, map. So as of now map is empty. Okay, now first I will come here, and I will just check whether my root is null or not. If it is root null, then I don't have any nodes in that particular tree, so I should return the empty. Okay, so in this case the our root is not null. So what we can do? So, and I will just check, okay, before going on to the other part. Okay, I will just check if the level, okay, level can is there in my map or not. So what is my level now? Level is 0, so which is not there, right? So I can say that, so just put level and put that particular node data. What is the node data here? It's a 4. Done. Now we have seen the traversal techniques, right? So let's move on to the another guy, okay, to the left side. Now while moving on to the left side, I should do level plus 1. So currently my level is 0. Now my current level is 1. So now I will just check first whether root is null or not. So root is not null. What does it mean? It means that it has some data, so we should traverse that. So before moving on to the next left and right, what should I do? I should just check whether this particular level has been already visited or not. Okay, and what is the level now? It's a 1. Okay, level is equal to 1 now. So here level is equal to 0. Now level 1 is not occurred earlier. So what does it mean? I'm visiting it for the first time. So I should put that. So what is the data? It's a 2. Okay, done. Now I will go to the left again. Now this time level is going to be 2. Now this level is not occurred earlier, not visited earlier. So I will do 2 and 1. Now both are empty, so no need to traverse them. Then I will go to the top again, and then I will go to the right. Okay, right. Now what is the level here? Again, it's a level is 2. Okay, so currently here a level is 1. From this particular node we have called level plus 1, so it is level is equal to 2. Now tell me, if I search, level is already occurred, so 2 level is already there, so I should not modify the value. Okay, I can just ignore that and will continue with my process. So there is no right and no left. There is no right, there is no left. So I will go to the top, down, and I will go here. Now from level 0 here, now it's a level 0 plus 1. It is going to be level 1 here, right? Now I can say that, is there level 1 in my map? Yes, already there. So I won't do any modification over there. So simply go to there. So again, it's a level 2. So level 2 there. Yes, level 2 there. Now again I have left here, so I will come here. So it's a level 3 now. Now tell me, is there level 3 in my map? No, not exist. So what I can do? Level 3, like a 3 key, and it's a 9. Done. Now I don't have any left and right, so I can simply go here, and from here there is no right and left. Okay, I can again come here, and I can go here. So from level 1 plus 1, it's a level 2. Now already level 2 has been occurred, so I won't modify that. So there is no left, no right here. Okay, done. So I'm done with visiting all the trees. Okay, now what are all the values are there in my map? 4, 2, 1, 9. Is this what the left view of a binary tree which we have taken? Yes. So done. This is our answer, right? How? So are you able to do this on your own? Now just try for so we have wrote this thing for left view. Now try for right view. Try for right view. So what is happening for the right view? So you need to store the node data which is been occurred at the last, which is visiting at the last. So when can we visit at the last? So it is what so whatever the data you are seeing, whether it irrespective of it is already visited or not, you need to keep on modifying your data, right? Let's try it out as well. So we'll take the same thing, 4, 2, 6, 1, 3, 5, 7 and 3. Okay, now so here currently level is equal to 0. Let me put my map here. So now level 0 is not visited, so I will put that here, and my data is 4. Now I will go to the left side. Okay, now what is happening? I have been this is going to be level 1, and which is not occurred earlier, so I will put that as a 2. Now I will go to the level 2, which is also not visited so far, so I will put level 2 as 1. Okay, so there is no right, so I will go to the top. From here I will come here again, it is going to be level 2. Yes, level 2. Now I need to level 2 has already been visited, okay, for the first time, but we are searching for an element which is being visited at the last. So until whatever the data has been put so far, we need to modify that. Okay, so we'll modify this level 2 with the second value. Sorry, it's a 3 now. Okay, 3. Yeah, 3. Now we are done with this. So there is no left and no right here, so we'll go to the top. From here we'll go to the here. Now we are done with this as well, so we'll go to the right side. Now this is time for the level 1. Okay, level 1 has been already occurred, right? So what we need to do, we need to modify the data as to the 6. Yes, done. Now again we'll come to the left side. Okay, if I come to the left side, it is going to be level 2. So level 2 has already been occurred, but I need to modify that, modify to the 5. Now again I have left, so it's going to be level 3. Level 3 is not occurred earlier, so I will put level 3 as 9, and there is no left, no right, so I will go to the top. Now from here I will go to the right, so there is no right, so from here I will go to the top, and from here I will go to the right. Now this time it is going to be level 2, so level 2 has already been occurred, but I need to modify that to the data currently, which is 7. Okay, which is 7. Now done. There is no left, no right. Okay, go to the top, and from here I am done with this. Go to the top, and this is what I have. So what is the data I have? 4, 6, 7, 9. Is this my right view? Yes, I'm done. Okay, if you want to write this as a code, you can simply write this as something like this. Okay, let's say left view, and I am taking a root and a level. Okay, and I will just check if root double equal to null. What does it mean? You should return simply 0. That's it. Else, like if not, you need to check whether your map contains the particular level or not. So map dot contains is for Java. If you are C++ coder, it is going to be this find. Okay, contains a level, so it will return either true or false here. So if it is contains, then it should return true. Okay, So when and only if you get false, then you need to put, okay, mp dot put what is the level, comma, root data. Okay, and in all other cases you need to go the left, left, and left. While moving on to the left, then you say left view or root to the left and a level +1. So here it's a point. Okay, so since it's a Java, it's in class based. Okay, now it's a, if you are moving right, left view root dot right and level +1. So at the end just return. Okay, like this map is going to be either you can pass it as a reference, or you can take that as a global variable. So at the end you can traverse through all the values which are there in the map, then you will get it. Okay, this is one way. Okay, this is one way. There is another way where you can maintain a global variable. Okay, global variable called max level. So you know that you will be visiting each node for the first time. So if you're you will be initializing your max level as -1 in the beginning, and if you are visiting like so instead of this particular code, you can just check if your max level less than current level. Okay, so you have initialized max as global variable. Okay, then what you can do, you can update your max level equal to current level, and you can you can just print cout root data. Or if they ask you to return all the left view nodes in the form of a vector, then you can just create a take a vector like output dot pushback root data. Okay, so in this case you are not using an extra memory here. Okay, so you are eliminating this map, that's it. And you guys know sometimes a map will take login time. So in this case, yeah, it mostly big of 1, but yeah. And this is using DFS technique. Okay, and if you wanted to use BFS technique, even that you can try out as well. So in this case you will be using Q. Okay, so try it out. Okay, we have discussed how to print all the nodes using BFS technique, right? So try it for this particular problem. Now let's move on to the next problem. Yes, what is a graph data structure? What is a graph? So a graph is a type of nonlinear data structure that consists of vertices and nodes connected by a edges or links for storing data. Okay, edges connecting the nodes may be directed or undirected. So here we'll discuss that. Okay, so here let me draw the same thing again. So A, then A to B, and A to E, C. Okay, now this is a graph. You can consider this as one area in your city, and you can consider this as one area, this as one area, this as one area, and this as one area. So now let's try to relate this thing. Okay, if you are standing at area some A, okay, now from this you will be having two choices. Okay, two streets. Okay, if you are standing in a circle, you will be having two choices. Either if you can go in this particular path, you can reach to the B. If you go in this particular street, you will reach to the E. Okay, so again from E, again you have a path to the D. Okay, you can either reach to D, okay, or A. So if you come back in the same path which you have ended, okay, which you have came till now, and from B, if you have visited in this particular path, for B as well, you can, if you follow the same path which you have came in, then you will be reaching to the A, and if you have chosen different path, you will be reaching to the C. Now from D as well, you have three choices, either B, E, C. So you can, again you will be having two choices, either you can go to the B or you can go to the C, and you can traverse to the same path which you have coming from. Okay, so here you can consider this as a edge. This is called as a edge. What is this? So this edge helps us to connect the two vertices or two nodes. Okay, this is called as an either vertex or a node. Okay, now this is what a graph means. And yeah, we have seen directed and indirected. So basically a graph will be of two types. Okay, a directed graph, undirected graph. What does this mean? Okay, so directed means, let's say I have all the edges which are representing some path. So so now here there is some directions, right, where edge is representing 2. So from A now you can go to only to the B. Okay, you can't go to the E because there is no path here. So the path here is you can traverse from E to A only. Okay, so you can see this arrow marks, right? So this arrow mark represents the directions which you can traverse through. So this is called directed graph, and this is called undirected graph. Undirected, it is a directed. Okay, so directed means where your edges will be pointing to the node which you can traverse from the current vertex, and undirected graph won't have any directions. It means like it's a bidirectional. You can either go and you can come back on the same path. Okay, that's it. And the next question is, what are the applications of data structure, graph data structure? So which means where can we use graph data structure? So graphs are used in a wide varieties of applications. Some of them are as follows. Social network graphs to determine flow of information in social media websites like Facebook, LinkedIn. So this is the one of the major application of a graph data structure. What it is? Social media. What is social media? How graph is being used in social media? So everyone uses social media nowadays. Even I know, like when I was in my very first year, I don't even know. I use Facebook, but I don't know what is being happening over there. So whenever I was started studying graph, I got to know that yes, this is the algorithm where they were using. So now let's say profile A. Okay, there is a profile A, and profile A has around let's say 2 friends. Okay, let's put it as a undirectional only. So 3 friends, B, C and D, and again B will have a few more friends. Yes, so let's say you can call them as a E, F, and even B and C are also a friends. Okay, now a C and like C has few friends. Okay, H and D and a G. Now, so how does a social media work? So let's say A has posted one post. Okay, so A has posted some photo. Now it will reach to the B, C and D. Okay, suppose B has liked this particular post or commented this particular post. Now this particular post will be shown to the E, F, means all the people, all the connections of a B as well. So this is how a social media work. Suppose if D has commented or posted your post, okay, A's post, then the friends of D can see the post. Okay, the friends of this is how connection has been made. Okay, this is how social media is being working. Even the one of the major application of graph is Google Maps. Let's say we have a Bangalore and Mumbai and some Hyderabad and Pune, and these are all the cities that you have, and you need to go to the Goa, let's assume. Okay, so I don't know what is a minimum path, but let's assume few things. So from Bangalore to I just wanted to go to the Goa. Okay, now let's assume the path is I need to come to the Mumbai and I can go to the Goa. Now let's say Mumbai to Bangalore, it will take 2 hours of flight journey, and from Mumbai to Goa it will take 2 hours of flight journey. And there is another option for me. If I can come to Pune, then from Pune as well I can go to Goa. So let's say from Bangalore to Pune it will take 3 hours. So and Pune to Goa it will take 2 hours again. Now from there is another path. Okay, from Bangalore to Hyderabad it will take 1 hour, and Hyderabad to Goa it will take 2 hours. Now my question is, if I take which path, I can reach the Goa in minimal time. Now this is the question. Okay, the answer is up to you. Okay, this is how a Google Maps works, right? So where you will be having different options, but Google Map is suggesting you the best path, okay, that you can reach your end destination in a minimal time, right? So here in this way you will choose this particular path, right? From Bangalore you go to the Hyderabad, from Hyderabad you go to the Goa. So here what is the amount of time that you are taking? It's at 3 hours, which is the minimum among all the path. If you have went in this particular path, it should have taken 4 hours. If you have taken this particular path, it could have taken 5 hours. So if you are following this particular path, it will take 3 hours. So this is how a Google Maps works, and this is where your graph data structure comes into picture. So this is called as an shortest distance as well. Okay, you will be having different algorithms for this, like Dijkstra. Okay, and yeah, so you will be having different options right there, and we will be having different algorithms as well. Based upon that, it will be recommending you the minimum time. Okay, so and second one is neural networks graph, where a nodes represent neurons and edge represents synapses between them. So neural networks are the one of the applications of artificial intelligence, or category of artificial intelligence. In that as well we will be using concept of graph data structure. And transport grids, where stations are the nodes and routes are the edges of the graphs. So this is the example which we have shown. And power or water utility graphs, where vertices are connection points and edge the wire or pipes connecting them. So this is a true real world problem. Okay, so like a water line or a power lines. Okay, and the shortest distance between two endpoint algorithms. So this is where, so if I wanted to go to Goa from Bangalore, so this is where shortest distance come picture. Now let's see the next question. So how do you represent a graph? So yeah, we have two ways to represent a graph. One is adjacency matrix and another one is adjacency list. So adjacency matrix will contain only zeros and ones, okay, where a 0 represents there exists a edge, and the 0 exists represents no edge. Okay, if you observe here, so we have a P, Q, R, S, T. Okay, now we will be taking like vertices into a vertices matrix. Like if you taken this example, we will be having 5 vertices and we will be having 5, so we need to take 5 into 5 matrix. So PQRST, PQRST. Now wherever there exists a path, just put it as a 1 over there. So P to Q, there exists a path, so P to Q you will put 1. And also since it's a direction, okay, undirected graph, you need to put the both the cases, like P to Q, Q to P. Okay, so Q to P as well you will put a 1. Okay, now this is how you fill this particular matrix. And there is another way. Okay, what is that way? So is adjacency list. So mostly people prefer this over adjacent matrix over matrix. Okay, it's an easy to accessible and little efficient as well. So here what is the thing? So you will take an hash map, like kind of vector of array. Okay, let's say if you have taken an array like this, so where you will be having all your vertices like PQ or ST. Okay, then you will create a vector here for each node where you will be putting all your path. Okay, from P to Q you can go, from P you can go to Q as well. So you will create Q. Okay, and it's a directed graph. Okay, there is, okay, so yeah, this is a directed graph, means you can go to the only the way which where your arrow will be pointing towards. Okay, now from P you can go to R as well. Okay, so you will put a R here. That's about the P. Now let's go to the R. Okay, so from R you can go to the S. That's the only choice you have, so S. Now from Q you can go to S, you can go to T. Okay, S and T. Done. 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 Now from S you can go to P, you can go to S itself. Okay, so you can go to P, you can go to S, and you can go to T as well. Okay, and from T you can't go anywhere, so it's an end here. Okay, this is how an adjacency list looks like. Okay, now we'll try to code all of these whatever we have seen so far, and also there is a concept called graph traversal techniques. Okay, so what is this graph traversal techniques? Graph traversal techniques. So these graph traversal techniques are DFS and BFS. What are these? So we will be given this graph, right? Like how to traverse through entire graph. Okay, traverse means where we can go to each and every node in case of graph. Okay, so for that we will be having two approaches. One is DFS and one is BFS. So a DFS follows a recursive approach and BFS follows an iterative approach. And a BFS uses data structure called queue, and a DFS, since it's an recursive approach, it will use a stack. Okay, now we'll try to understand what is this traversal techniques and how to how to code them, and how to represent our graph in adjacency matrix and adjacency list. In this tutorial we will be learning about graph traversal algorithms, namely breadth first search and depth first search. So coming to prerequisites, it will be good if you know how to represent a graph using either Java or C++. But in this particular video, I will be coding in C++. Okay. So yeah, without wasting any time, let's get started. Before starting, if you are visiting channel for the first time, please don't forget to subscribe. And if you like the content, please hit that like button up. And if you have any queries or questions, please let us know in the comment section. Now let's first discuss a breadth first search, then we'll see depth first search. Okay, so probably if you have seen my earlier video which was on trees, you might end up hearing this word called a BFS over there. So yes, like what is the difference? So in this video we will be talking about graph. So the same topic now, BFS. So there also BFS, here also BFS, both are same, right? No. Okay, so these are all different because the data structure has been different. So trees and graphs. So again, so you might, if you know what is a graph earlier, so you might think that yes, we do have nodes here, we do have adjacencies here, like we do have edges, and we will travel from one edge node to another node. Okay, that's it, right? So yes, but the difference is in trees usually there will be no cycles. So what is a cycle? Let's say you have a node like this. Okay, you have a tree something like this. So now you will start visiting from here. Okay, you will go here, then you will go here, then you will go here, again you will come here again. So it is never ending process, right? Just because of the fact that you never see a route which is a null, right? So it will go in an infinite loop or infinite recursive calls. Now what is the solution? So basically, so you won't see this kind of situation in trees. Okay, but in graphs we do have that situation. Okay, so where you will be having cyclic graphs. Okay, so graphs are being, we have a different graphs, okay, directed, undirected, cyclic and acyclic graphs. So here we need to handle both, okay. So for that we are having something special for graphs, okay. So let's see. So first we'll see one example where we can find BFS for that particular graph. We'll see couple of examples until we get some familiar about how BFS works in a graph. Then we'll jump on to the logical. Then we'll see coding part. Okay, let's start. So let's see. We have a graph like this. So 1 and 2, then 4 and 5. Okay, so from here you will have a, so here, then here. Okay, now first you will start from here 1. Okay, you will visit this guy and let's assume this is your output. Okay, now tell me what are all the adjacents to the 1. These are all the adjacents. So what is meant by adjacents? So the nodes or vertices. So basically we call these particular things as a vertices in a graph. In tree we call them as a nodes. Okay, so here can I say there is some path from 1 to 2 and 1 to 3. So if there exists a path, then I can say that they are adjacencies. Okay, so from 1 there is a path from 2. Okay, from 1 there is a path to 2 and 3. So I will first visit 1, then I will go to 2, then I will visit 3. Okay, then now what is the next element? So I will go to 2. Okay, and I will travels. Okay, I will go to all the adjacencies of 2. Okay, what are all the adjacencies of a 2? It's a 4, 5 and 1. Okay, so did we visited 1 already? Yes, we have seen 1 already. So we'll print 4 and 5. Done. So now we will go to 3. So what are all the adjacencies of 3? It's a 1 and 5. So we have visited 1 already here, and we have also visited 5. 2 done, 3 done, 1 done, 4 done, 5 done. Okay, so we have visited 5 as well. Okay, now you will go to 4. Okay, what are all the adjacents of a 4? 2, 5 or 6. Okay, so you have visited 2, you have visited 5, right? So you will left with 6. So you will add a visit here, like you will visit that particular 6 now. Now it's a 5. So what are all the adjacents of a 5? 3, 6, 4, 2. Okay, 3, 6, 4, 2. So you are done with 2, you are done with 3, you are done with 4, you are done with 6. So you won't add anything. Okay, from you will at last you will come to 6. What is a 6? So what are all the adjacents of a 6? 4, 5. Okay, so you have visited 4 already, you have visited 5 already. So can I say that now on this node I have visited all the nodes, visited all nodes, all vertices. Done. Okay, so hope you got some idea how BFS works. Now we'll see another example. Okay, another good example, so that you will get some clear picture about how this BFS algorithm works. Okay, so let's take another tree and we'll see. So graph, sorry, 1 have 2 and 3, and for 2 you have a 4, and for 2 there is a 5 as well, and there is a cycle, and you have another node. Yeah, and surprisingly we have another graph here. Let's say 7 and 8. Okay, 7 and 8. So is this a valid graph? You might have that question, is this a valid graph? Yes, this is a valid graph. So basically this entire graph will cause a one component, and this one entire graph will cause another component graph. Okay, so there will be a lot of questions, like there is some important questions based upon this component graphs. Okay, so hopefully we'll see them in next videos. So here now let's say I will start with 1. Okay, I will start with 1. So I will put a 1 here. Now what are all the adjacents to the 1? Say 2 and 3. So I will pick up a 2. Now I will go to all the adjacents of a 2. So who are all the 3. So now I will go to adjacents of 3. So it's a 5, 4, 1. Okay, so 1 is already visited, 5 and 4. So you will have a 5 and 4. Done. So I have completed 1, I have completed 2. Now I have 3. So 1, 4, that's it, right? So I have already visited 1, I have already visited 4. So I'm done with 3. So now I will go to 5. So for 5, who are all the adjacents? It's a 2, 4, 6. Okay, 2, 4, 6. So 2 already done, 4 already done. So there is only left with 6. We'll add that. Now we'll go to 4. Okay, so for 4, 2, 5, 6, 3. Okay, 2 done, 3 done, 5 done, 6 done. Okay, there is nothing to add. Now we'll go to 6. Okay, so for 6, who are all the adjacents? 5 and 4. Okay, 4 done, 5 done. Okay, so on this note, I'm done. So there is nothing to visit again. Now here, one thing. So is this also a graph? We need to traverse this as well. Okay, so I will again start from this node. Okay, so then I will add 7. Okay, now who are all the adjacents to the 7? It's a 8. Now we'll complete at 7 and now we'll go to 8. So is there anything connected to the 8? Yes, it's a 7. So already 7 is visited. So we are done with here. Now there is nothing to add to the next. So this is how it works. Okay, now let's see how our logic will be for BFS. Okay, so listen carefully. So which is very important concept for any interviews if you are attempting, like if you are attempting some good product based companies, these are all the questions that are going to target. Okay, you might think that this is just an traversal algorithm. Don't think like that. This is beyond that. Okay, this is beyond that. You can solve a lot of problems using this particular BFS and DFS algorithms in a graph. Okay, now let's take one good graph and we'll try to build our logic by using that graph. Okay, let's say I have it graph something like this: 1, then 2, 3, 4. Okay, I will have 5, 6 and 7, 8, 9. Okay, so from here, here, here. Okay, so first thing, so whenever you have given a graph, you need to draw an adjacency list. Okay, you need to form an adjacency list of that particular graph. So you might be wondering what is adjacency list. So you can consider, if you are a C++ coder, so you might think as a vector of list. Okay, and generally there were two ways to represent a graph. So one is adjacency matrix and another one is adjacency list. So in adjacency matrix, you will represent the graph in terms of ones and zeros, where you will be taking vertices to the vertices. Okay, so how many, like if there were 9 vertices in a graph, you will take 9 columns and 9 rows. It's a 9 by 9 matrix. And you will be, if there is a path from one particular vertices to one particular vertices, let's say 1, 2, 3, you will represent a 1 over there. If there is no path between 1 and 3, you will represent 0. Okay, so it contains only zeros and ones. Okay, so that is how adjacency matrix is going to look like. And while coming to adjacency list, so here you will be having a vector of list. Okay, let's see how. So adjacency list. So basically, let's say you will pick up node 1, okay, vertices 1, and tell me who are all the adjacents to the particular vertices, like 1, so 2, 4, right? 2, 1, 4. You are done with 1. Now you will go to next, you will go to 2. Who are all the adjacents to the 1, 2, sorry. So 1, 3 and 5. You will have completed this. Now you will go to 3. Who are all the adjacents to the 3? It's a 2, 7, 4. 2, 7, 4. Now we will go to next one, this 4. Who are all the adjacents to the 4? So 1, 3. 1, 3. Then you will go to 5. It's a 2, 6. Now you will go to 6. It's a 5, 7. Now we will go to 7. It's a 3, 8, 6. Now we will go to a 8. So it's a 7, 9. Then you will go to a 9. It's a 8. Okay, so from 7 you have 3. Okay, done. So this is the adjacency list looks like. So you can call this as a, or you can consider this as a vector index. Okay, so one index, and for one index you will be having a list. Okay, list means you can consider this array. Okay, vector of array. So where you will be having 2, 4 and all. Okay, so the idea is we will stick to that particular vertex. Okay, then you will traverse to that particular array, so that you will get an all the adjacencies of that particular vertex. So that's it. So now we'll see how we will implement BFS by using this for this particular graph. Okay, so you will have a visited array or vector. Why this? So earlier, so what is the problem that we have identified in trees? So you are visiting the same node for the multiple times. Okay, so the same thing happens in graph as well. Yes, right? Don't you think? Yes. So to reduce that particular problem, we are having a visitor array where you will be keeping all the visited vertices. Okay, so with zeros and ones. Okay, you can consider 0 means not visited, 1 means visited. So by default, we will be filling them with zeros. By means that we are not visited. Okay, so how much indexes we need to take? So it will be, so if you have n vertices, you need to take n plus 1 vector array, just because of the fact that we will be starting from the 1th index, 1th vertices. Okay, so let's take an array, looks like this. So we do have 9 vertices, so I have to take 10. Okay, so starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this. Okay, now you will fill all the zeros over there. You can consider, okay, if you don't like consuming a lot of memory, you can use a bool as well, which takes 1 byte only. Okay, for bool you can consider false as an not visited and 1 as a visited, sorry, true as a visited. And also you will be having another thing, what is called a queue data structure. What is a queue? A queue is a data structure which follows the principles of first in, first out. Like whoever comes into the first, they will go out first. That's it. Okay, now we'll see how that works. Okay, so this is a queue and this is a visitor array. Okay, so first we'll start with this one. Now tell me, is that one visited? No. So what you will do? So you will call a BFS, like assume like that. Okay, so now you are visited, sorry, in BFS. Now we will mark this guy, this particular one as a visited. Okay, one as visited, so 1. Now you will enqueue this particular vertex into the queue. Okay, you will say 1. Okay, done. Now what I need to do? I need to visit all the adjacents of a 1, right? So I will iterate in a loop. Okay, so I will enqueue all the adjacencies of this 1. Okay, if they are not visited. Okay, if they are visited, no problems, they will be in my output, right? So if they are not visited, I will push enqueue all of them into my queue. So it will be first 2, then 4. So on this note, I can say that I'm done with 1. So whenever I am done with this particular guy, I will push that into my output, like I will print that into my output. So let's say this is my output. Okay, so 1, I got 1. Now is that queue empty? No. I will pick up this guy and I will visit all the adjacents of that particular vertices. Now before that, what I will do, I will mark this guy as a visited. Okay, so 2. Okay, here 1. Now I will enqueue all the adjacents of a 2. So what are all they? 1, 3, 5. 1 is already visited, right? 1 is already visited. Is 3 visited? No. So I will push that 3. Now is that 5 visited? No. So I will push 5 as well. Done. Now what I will do? So on that node, I can say that I am done with the 2. So I will erase that. Okay. Now the next one is 4. Okay. So first I will mark 4 as a visited. Now I will go through all the adjacents of a 4. So who are all the adjacents of a 4? It's a 1 and 3. So is 1 already visited? Yes, already visited. Okay, so sorry, I forgot to overwrite this. Yeah. Okay, so now 1 already visited. Yes. So is 3 already visited? Yes. Is 3 also visited, right? So you are done with 4. So you will print output that. Now you will come to 3. Okay. Now what are all the adjacents to the 3? 2, 7, 4. Okay. Is 2 visited? Yes. 2 is already visited. Then 7 is visited, no, so you will mark 7 as a visited and push it to the queue. Now is 4 visited? Yes, 4 is already visited. Okay, so you don't need to worry about that. You have completed this and this. Okay, so you are done with 3 and you will add the output. Now 5. So who are all the adjacents to the 5? 2, 1, 6. Is 2 visited? Yes, it's already visited. So no work with 2. Is 6 visited? No. So you will mark it as a visited and you will push it to queue. Now, so you are done with 5 as well. So I will print it to the output board. Okay. Now it says 7. For all the adjacents to the 7, 3. So 3 done. Yes, already visited. So is 8 visited? No. So you will mark it as a visited and push it to the queue. Now 6 already visited. No work. Okay. Done. So I am done with 7 as well. So I will print it to my output board. Now 6. So who are all the adjacents to the 6? It's a 5 and 7. 5 already visited. Yes. 7 already visited. Yes. Okay, no work. So you are done with 6 as well. Okay, we'll print 6 here. Done. Now it's a 8. Who are all the adjacents of 8? 7 and 9. So 7 already visited. Yes. So no work. So is 9 visited? No. So you will mark it as a visited and you will push that to the queue. And on this note, you can say I'm done with 8. Okay, so you will put that in the output board. Now it's a 9. Okay, so who are all the adjacents to the 9? It's a 8. So is 8 visited? Yes, it's a visited. So no work. So on that note, I can say that I'm done with 9 as well. So did we covered all the vertices? Let's see. Okay, so did I visited 1? Yes. 2? Yes. 3? Yes. 4? Yes. 5? Yes. 7? Yes. 6? Yes. 8? 9. Done. So this is how binary best first search algorithm looks like. Okay, so without wasting any time, let's go on code for this particular approach. So now let's discuss the C++ code of an BFS algo. Now first we will be taking 2 inputs from the user. One is vertices and the edges. So vertices are the number of vertices we will be having in particular graph. And again, I am saying that it's an 1 based indexing graph. Okay, so means I will be starting the vertices names from 1. Okay, now edges. So why we need edges? So it will represent the how many edges we are having in entire graph, so that we can iterate that many times and we can form an adjacency list. Okay, so we'll see that now. So for that, to form an adjacency list, I will be creating array of vector. Okay, where so for one particular array we will be having indexes, right? So how many indexes we will be having? So vertices are 9. Okay, so since we are considering 1 based indexing, we will be using vertices plus 1. Okay, plus 1, and then it's a vector. Okay, so here in loop we are iterating throughout the number of edges we will be having, and for every time we will be taking 2 inputs. One is from vertex, another one is a 2 vertex. Okay, so we will be taking that and we will be forming an graph adjacency. So why 2? So you are forming U to V and V to U. So why? So basically, since it's an undirected graph, okay, so we might have an both sides, right? So let's say I have a path from 1 to 2. It is equivalently to 2 to 1 as well, right? So that's why it's okay if you use only one thing, like if you form only one edge, that's totally okay. Okay, not a big problem. Now let's see. So now I'm assuming that you have a adjacency list, okay, which is having all the edges. Now we will be having a visited vector. So where initially we will be storing all the zeros. Okay, initially we will be storing all the zeros in it. Now we will be starting from the 1. Okay, always my starting point is 1. So I represent the BFS starts from 1. So here I am passing visited vector and adjacency list. Okay, now I will go here. Now here what happened? So first whatever I started like, so I will make that start as visited first, right? 1 represents visited, 0 represents not visited. So I will make it as a 1. Then I will create a queue. Okay, in that queue I will firstly push that starting point. Okay, now I will iterate through the queue until that queue is empty. Okay, so since my queue is not empty now, I will enter into the loop and I will make an friend. Like what is a friend happens? So it will give me the top element. Okay, so first element. So what is the first element? It's a 1 now. So my current vertices is 1. Now I will pop that one, so I will remove that. Okay, now I will print that onto my output screen. Now I will iterate throughout that, like I will move to all the adjacents of that current vertex, right? 1. So this is how I can use now. So I will, let's assume, okay, so from 1 first vertex we do have a 2 and 3. Okay, first I will go to 2 and I will check whether if that is a visited or not. If that is a visited, it could have been a 1. If that is not, a 0. So if it is 0, I will enter into this particular if block. Okay, now if it is 0, what I will do? I will first mark it as a visited, then I will push it to my queue, right? I am doing that. I will go to 3. Okay, now I will do the same. Okay, now after doing, I will come here again loop. Okay, so my queue is not empty, so again I will repeat the same for current value vertex is 2 now, right? So I have popped out that 1. Okay, so it will do all these things until this queue is empty. When this will become empty, it will become empty when all the vertices are visited. Okay, so what visited vector will become 1, all ones. Okay, so this is how a code looks like for a normal BFS, like if it's a component graph. But we have discussed something different, right? What is that something different? So here you might have a graph like this. So here, right? So I will pass 1 here and I will done with this particular graph. Now what about this graph? So I have to repeat the same again, right? I need to repeat the again. So since I don't know what is the starting point, always. So what I will do now, I will return a loop. Okay, let's say, which will start from 0 and goes on till vertex plus 1. Okay, and I will check if that particular I is visited. If it is not visited, okay, I will go. Okay, so first 1, okay, I will go. I will call BFS and visited and adjacents. Done. Okay, so I will visit all this graph, right? I'm done with this graph. Now again come. So I will come after this loop and I will say increment to 1 to 2. So I will make my 1 as 2 now. So 2 is already visited. Yes, it's visited. So why? So I am passing this visit as my reference. Okay, so whenever it will visited, it will get updated here as well, and I will mark it as 1. So 3 visited, 4 visited, now 5. I is 5 now. So is 5 visited now? No, 5 is not visited. So what I will do, I will make a call to BFS. Okay, now it will do this thing. So again I will come back and I will say 6 already visited. Done. So this is how code looks like. Okay, so nothing much. Okay, so it's just an loop. So I will remove that here and I will make int I equal to 1 and I will say iterate to vertices I plus plus. Okay, so if visited of I is not equal to 0, if not equal to 1, I need to say BFS of I and visited and adjacency. That's it. This is how the code looks like. Okay, so if you are in an interview, it will be good. Okay, so interviewer expects you to write this coding like algo to have in multiple components. But if you are still have that doubt what to write, you can ask your interviewer. Okay, so can I assume, is there only one component in this graph or multiple components exist? Okay, so the complexity of this approach looks like, you can guess, right? So yeah, it will be mostly big O of n since we are visiting all the vertices. And you might think, yes, we are doing for couple of times, right? So we are calling here and we are having, in worst case we will be, so let's say it's a one component, then it will be big O of n first time. Now again I am calling all these vertices. So you might think it's a big O of n plus 1, n into n. But if you carefully observe, it will end up at n plus n. Okay, so I can say that max it will be big O of n. And coming to space complexity, so here you will be using this, okay, visitor array. So for that you will be using big O of n, like big O of vertices, number of vertices. Then also you are using a queue here, right? A queue. So again, at worst, it might take big O of n, right? So you can have a big O of n plus 1. It will be, you can say that, but it's okay. So if you can say big O of n as well, okay, be accurate. Okay, so try to figure it on your own. Okay, that will be a good practice. Okay, cool. Now let's discuss the DFS. What is a DFS? A depth first search. Depth. Okay, depth. Okay, let's see. Okay, so we'll consider a small graph. Okay, so 1, and from 1 to 3, and from 2 it's a 4, and it's a 5, and 3 to 5, and here. Okay, so this is a graph you have given, and you asked you to find the DFS of this particular graph. So how do you start? So let's say we'll start from 1. Okay, I will say 1. Now, so in BFS we have moved simultaneously to all the adjacents of a particular vertex, but in DFS we don't do that. We'll pick up one of its adjacent and we'll traverse all of its particular adjacents. Okay, so like let's say, so now what are all the adjacents of a 1? Say either 2 and 3. Okay, we'll pick up 2 first. Okay, now we'll pick up 2. Okay, so from 2, what are all the adjacents to the 2? 4 and 1. Is 1 already visited? Yes, it's already visited, so we don't need that. So we'll say we'll go to 4 now. Now from 4, what are all the possible adjacents? 2, 3, 5, 6. Right? Now is 3 visited? No. So you will say I will go to 3. Now I am currently here. Now what are all the adjacencies of a 3? It's a 1, 5, 4. So 4 already visited, 1 already visited. Now I'll go to 5. Now from 5, who are all the adjacents of a 5? 3, 4, 6. 3 already visited, 4 already visited. Now I will go to 6. So from 6, is there any unvisited? Is there like what are all the adjacents? It's a 4, 5. So 4 is already visited, 5 is already visited. So nothing to go. Okay. Now I will check all other vertices where I left. Okay. So in this way, it looks like this is the DFS of this particular graph. Is there any other solution? Yes. So at beginning, instead of going at the 2, I will go at the 3 now. Okay. So first I will visit 1, then I will go to 3 path. Now what is the from 3? What are all the possible ways we have? I can go to 1, I can go to 5, I can go to 4. So now I will pick up, I say I know that 1 is already visited. Now I have to go either 4 or 5. So I will go to 5. Okay. Now from 5, what are all the adjacencies? 3, 4, 6. Okay. Now I know that 3 is already visited. Okay. 3 is already visited. Now I can choose 6 now. I will choose 6. Okay. Now from 6, I have 5, 4. Okay. 5 is already visited. Okay. I will go to 4. Okay. I will go to 4. Now currently I am at here. Now what are all the adjacencies of 4? 2, 3, 5, 6. Okay. So 3 visited, 5 visited, 6 visited. So I will go to 2. Okay. So from 2, I will go to either 4 or 1. Okay. So since both are already visited, I can stop here. That's it. So this is also an correct solution. Okay. So on this note, I can say that there might be a different solutions for one particular graph. Okay. So it depends upon how you are going and what text you are currently picking up. Okay. So now let's simply jump into our logic. Okay. So I will take up simple a graph. Let's say I have a 1, then 2, then 3, 4, 5, 6. So this is one component. Have another component, let's say 7 and 8. Okay. So now first step, we need to find the adjacency of this particular graph, adjacency list. So how does it looks like? So we have first one index. So first vertex, who are all the adjacents of the first? 2, 3. So and for 2, it's a 1, 4. And for 3, it's a 1, 5. And for 4, it's a 2, 6, 5. And for a 5, it's a 3, 4. And for 6, it's a 4. For 7, it's a 8. And 8, it's a 7. Okay. This is the adjacency of this particular graph. Now let's see. So first thing is first, we do have one visited array, okay, where it will be by default it will be marked as all the zeros. So here, since we have 8 vertices, it will be 8 plus 1, it's a totally 9. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay, so let's write the indexes of this. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, now so all these were filled with zeros. Yeah. Now how this works? Now basically this DFS is a recursive algorithm. Okay, so if you are in an interview, they are not interested in recursive manner, so you know how to write, right? By using stack. Okay, you can write this in an iterator approach by using stack. Okay, but let's see. Okay, so I will tell you recursive approach, but it's your job to write the iterative approach. Okay, so it's very easy. I gave a hint, right? Try it on your own. So let's say first I will start from 1. Okay, so while discussing the code of BFS, I have shown you how to, if the given graph is an component based graph, so if you have different components, I have shown you how to traverse to that, right? So for I is equal to 1 to vertices plus 1. Okay, if that vertex is not visited, I can say that do DFS of that particular vertex. That's it. Okay, this is how it looks like. So first we'll start from a DFS of a 1. Okay, so from here, what are all the ways? So I have 2 and 3. Okay, I have 2 and 3. So I will pick up this time, I will go with 2 side. Okay, so DFS of 2. So before moving on to DFS of 2, I will mark DFS 1 as visited. 1 as visited. Now since I started 2, I will mark it as a visited. Okay, now from 2, where I can go? Okay, so on my output board I can say that till now I have 1 and 2. Okay, so now again what are the adjacencies of 2? It's a 1 and 4. Okay, so I know that 1 is already visited and I will go with 4 now. So DFS of 4. Okay, cool. 4 done, 2 done, 1 as well done. Okay, 1 is also visited. Now so from 4, who are all the adjacents? So before moving on, I will mark it as a visited. Now who are all the adjacents? It's a 2, 6, 5. Okay, since I know that 2 is already visited, okay, I will go with next element called 6. Okay, 6. So before moving on, I will mark it as a 1. DFS of 6. Okay, cool. Now who are all the adjacents of 6? It's a 4. Okay, I know that 4 is already visited, right? Visited. Now I will go with, so since we are here, so 6 we have been to 4. Okay, now for 4 we have been done with 6. Okay, so we come here. Okay, we'll come here. So for 4 we have another option called DFS of 5, right? So there is no going from here. So after 6 we have only 4. 4 is already visited, so we'll come back to the top like previous call and we'll go to the next adjacency of that particular vertices. So it's a 5. Okay, I will mark 5 as a 1 and I will go to the 5 now. So for 5 it's a 3 and 4. Okay, so first I will go to check with 3. So is 3 visited? No. So I will mark it as a visited and I will go DFS of 3. Okay, now how does it look like? So since I am at 3, who are all the adjacents of 3? It's a 1 and 5. Okay, 1 and 5. So 1 already visited, 5 already visited. Okay, 1 already visited and 5 already visited. So there is no mid away from 3. Okay, it's blocked. So I will go to top. So for 5, so 3 done and 4 left. So is 4 already visited? Yes, visited. Now again I will go to 4. So out of 4 is also done, 5 is also done. Now from top of the 4, I will go to 2. Okay, so is there anything left in 2? No. From again I will go here, there is nothing in here as well. Okay, so 3 we left with 3, so 3 is already visited. So till now we have on our output to 1, 2, 4, 6, 5, 3. Okay, so happens, stop. Okay, so this is what happens. Now what I will do? So I will go to my main now. So all this happens for first 1. Okay, so first iteration. So I is equal to first. Now what I will do, I will go with, I will increment my I to 2. Okay, so is 2 visited? Yes. 3 visited, 4 visited, 5 visited, 6 visited. Now currently I'm at 7. So 7 is not visited. Okay, what I will do, so I will make a call to DFS of a 7. Okay, so I will mark it as a visited and I will put it on my output. Now what happens, so from 7, who are all the adjacents? It's 8. I will make a DFS of 8, mark it as a 1. Okay, so from 8, who are all the adjacents? It's a 7. 7 is already visited. Okay, so block. Okay, I will come here. Is there anything to visit from 7? No. So I will return to main. So from main, I will increment my I. So it's 8 now. 8 is already visited. So that's it. Okay. So did we covered all the vertices? 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So I highly recommend you to take another graph and try out this approach. Okay. So it's very, very important. Okay. So now let's see the coding part of this particular DFS. Now let's discuss the C++ code of our DFS algorithm. So it's the same like before, like till creating an adjacency list, it's same as BFS. Okay, so we have seen that earlier. So till here, it's the same. Okay, so after we have adjacency list, we will be doing something different. Okay, so not much. Okay, so let's see. So first we will be having a vertices. Okay, so visited array. Okay, where we would be initializing with a 0 by default. If it is visited, we will be marking it as a 1. Okay, then so here I am assuming in case of components. Okay, we have different components to visit. Okay, so if it is not, it's very simple, right? So you will say a DFS of, you will start with 1 and you will go visited and you will go adjacent. That's it. So it's as simple as that. If since it is a different components, it has different components, I am making it as a for loop and I am traversing to all the vertices and I am checking if that particular vertex is visited. I won't go anywhere. If that particular is not visited, I will call DFS. Okay, so since 1 is not visited, I will call DFS for 1 and I will come here. Okay, I will come here. So since my start is 1, right? Then I will say, so I will take visited vector and adjacency. Now I will marking a visited of start as a 1 since I started visiting. So and I will print the start as well. Okay, now I will iterate through all the adjacents of a particular start. Okay, so let's see. So first I got let's say I have an adjacency from 1 to 2. So I will pick up 2 and I will start DFS. Okay, so here, so again I will go to make an recursive call for 2 and I will again start, right? So if there is a 2 has 3 and I will again start for 3. So it's gone like that. So since that is why it's called as a depth wise. Okay, so it will reach till the depth, so till the last vertex, and then if it does particular vertex doesn't have any next vertex to go, then it will make a call to come back. Okay, it will go to previous call, then it will go to previous, and it will from that previous call, if there is any adjacency to visit, then it will do that. Okay, so I will keep on doing that, and if that happens, okay, so I will come back here and now I'm done with 1. Now I will check with 2. Since 2 is visited, again 3 visited, 4 visited, 5 visited, 6 visited, 7. Yes. So hope you have remembered our example, right? 7 is not visited. So I will make a call to 7. So I will mark 7 as visited here. Okay. I will print 7 in my output board and I will go through all the adjacency of a 7. Okay. Now what is the adjacency of a 7? It's 8, right? So I know that it's a not visited, so I will make a call to DFS of 8. Okay, I will visit that again and I will mark it as a visit and I will print it on my output board, and from 8 there is only 7 which is already visited. Okay, nothing to go. Okay, so I will come back to this loop. That's how it works. Okay, so that's as simple as that. Okay, so again I'm saying that these two algorithms are very, very important in perspective of interviews. Okay, if you are aiming for the high, so please don't try to not to skip these algos. Okay, so please try to practice as much of problems you can. Okay, so the next question is, what is the difference between tree and graph data structure? Okay, so tree versus graph. So tree and graph are differentiated by fact that tree structure must be connected and can never have a loops, whereas in graph there are no restrictions. So the major difference between tree and graph is tree won't contain loops, okay, but graph can contain loops, okay, where like we will be calling them as a cyclic graphs, okay, a kind of thing. But trees won't contain graph, like trees won't contain loops forever. Tree provides insights on relationship between a nodes in a hierarchical manner, and graph follows a network model. So here in tree we will be following the hierarchical manner, right? Like structure, we have seen one example of file structure. But in graph we are not following the hierarchical structure, we will be following the network model, where one node is being connected to many other nodes, and that particular node is being connected to many other nodes, okay, like this. So this is the difference between graph and tree, okay. Now next question, what is the difference between breadth first search and depth first search? Okay, so both are traversal techniques only, okay, and but we'll see what is the difference, okay, major differences between both. So here BFS versus DFS, graph traversal techniques, graph traversal, but even it can be for tree and tree as well, okay. The main difference between DFS and BFS is the BFS travels by level, and whereas DFS travels by the starts from the starting node and reaches till the end node, okay, the leaf node, and then again it will go back to the starting node, then again come to the leaf node, okay. Let's say I will take one example, okay. So let's say if you have a tree like this, BFS follows this thing, okay. First it will complete all the level 0, then level 1, then level 2, but a DFS would works like this, okay. It will start first this particular node and it will complete this path, okay, this path, then again it will go back to the top and it will complete this path. Now again go back to the loop, like starting point, and again it will complete this path, and again go back to the root, and then it will complete this path, okay. So depth wise it will starts from the root node and then it will come to till the leaf node, and again it will go back to the another path, okay. This is another difference. So further BFS, yeah, so the data structure, the type of data structure it uses to compute the, like, traverse the graph. So BFS takes queue, which follows the first in first out logic, and DFS takes FIFO, which is like queue stack, LIFO stack, okay, last in first out. So DFS yields deeper solutions that are not optimal, but it works well when solution is dense, whereas the solutions for BFS are optimal, okay. So DFS solutions are not that much optimal because it will go on deep, like it will take out all the possible path, okay. It will consider all possible ways to solve a problem to reach till the end, to reach till the our solution. But whereas a BFS won't do that, okay. It will go in a linear manner and checks whether this is a what we are searching for or not, okay. That's it. Now the next question, how do you know when to use DFS over BFS? Yeah, very good question. So I have seen many areas where we can solve a problem using both a DFS and BFS solution, but often that selecting the which solution to write the code is also an like kind of much needed one in an interview, okay, because it matters a lot in searching, okay, finding the optimal solution. So probably this question would answer those questions. So the usage of DFS heavily depends upon the structure of the such tree or graph, the number of and locations of solutions needed. So following are the best cases where we can use DFS, okay. So if it is known that solution is not far from the root of the tree, a breadth first search might be the better. So they are telling that, okay, like if there is a tree like this and solution is what you are searching for is exist here. Now tell me, so DFS, if I follow DFS, it will come down till here, then okay, then it will come down here. So till now we have visited 4, right? 4, or we have visited like paths. Okay, if we have considered path, we have visited 5 nodes. Then we are going to the solution which we are searching for. But if I consider a BFS, I first complete this level, then I will complete this level. So to come to our solution, I have visited only 2 nodes, right? So now it's up to you. Okay, you guys know clearly seen what is an advantage of using a BFS in sometimes in these cases where our solution is very near to the root. Now, so second point, the tree is very deep and solutions are rare. Okay, like so the height of the tree is very big, okay, but solution is very rare. Then going for DFS, going for depth first search will extremely take longer time to compute the solution, which involves finding hell lot of ways to solve the problem. Okay, that is going to yield an big amount of time, okay, which is not efficient. Now if the tree is very wide, okay, like the width of the tree is very high, a BFS might need too much of memory. Yes, right. So if it has for each level, okay, if this is an n array, if it is an n array a binary tree, sorry, if it is an n array tree, so n array tree, it should looks like this, something like this. Okay, where each node will be having more than one node. Okay, like it's an infinite. Okay, a parent node can contain infinite number of child nodes, then it is called as an n-array tree. Okay, so in this case the width of the tree might be very high, right? So in this case, by going till depth breadth first wise will take a lot of space. Okay, so in this case going for DFS is a good option. So if solutions are frequent but located deep in the tree, we opt for DFS. Okay, they are saying that if your solutions are very rare and it might enter very if your solution might exist in very deep, means a very lower order, okay, then going for DFS is the right approach. Okay, it's just an opposite to the what we have discussed in the first point. Okay, now next question is, what is topological sorting in graph? So what is topological sorting, which is a very important algorithm. Okay, if you are preparing for companies like Amazon, so Amazon, this is one of the most frequently asked graph question in an Amazon. So it will be having different algorithm, like you can solve this problem using different algorithms like Khan algorithm. Okay, topological sorting itself is have one algorithm which follows both a BFS and DFS technique. Okay, so yeah, if you are aiming for such big companies, please have a look at this topological sorting algorithm. Okay, and this is one such problem you won't get afraid of, because most of the people feel that graph is a little complicated topic, but it is not. Okay, all you need is with some strong basics, then you can able to easily solve the graph problems. And one of the advantage of graph problems is, in an interview you will get only standard problems. Okay, like it's very rare, okay, I can say that it's very rare to get new problems, like unseen problems or unsolved problems, either in lead code or interview bit platform. Okay, so you will get only the frequently asked problems. Okay, because it's little tough to create an problems. Okay, so let's come to this topological sorting. So a topological sorting is a linear order of vertices such that every directed edge I, vertex I comes before joining ordering I. So I'm pretty much sure that you haven't understood that definition. So let me put down like this. Okay, so let's take it as a becoming a SDE. Okay, becoming a SDE. So let's say everyone end goal is to become SDE. Now to become SDE, we have different path. So one path is like to learn system designing first. So to learn system designing, you should be very good at algos. If you want to learn algo, then you should be very good at DS. It's like something like this. Okay. And if you want to be good at data structures, then you should learn OOPS. If you wanted to learn OOPS, you should pick up any OOPS language, either C++ or Java or Python. Done. Now you can, in this is one path where you can become software engineer. And there is another path, okay, to if you wanted to get into startups, okay, you can learn web development, okay. So, and you should learn some basic DSA as well. To learn basic DSA, you should learn programming language, either C++ or Java or JavaScript if you wanted to web dev. And you can become Android dev as well, Android or iOS. Then again, this is going to be same path. Okay, so this is an overview of like where you will be having different options, and you can become an SD. Now I wanted to sort this thing as a topological sorting. So the topological sorting means, let's say for everything, if I wanted to become a software engineer, if I would like to take out this particular path, what is the first thing that I need to do? I should learn programming language, C++, Java or Python. Then I should learn OOPS, then DS, then Algo, then SD, then SDE become. This is one way, right? And another way is learn C++ or Java or JavaScript and solve some basic DSA problems, then learn full stack development, then become SD. This is another path that you can become SD. What is another path? Learn either Android or iOS and learn some basic DSA. Then so yeah, here it is an C++ Java kind of. Okay, so C++ or Java or JavaScript or some Kotlin, which are Android languages, or Flutter, and solve some basic DSA, then become SD. So to become an SD, these are all the paths that you need to consider. Okay, and this is called a topological sorting means. Okay, so here I can say that to become an SDE, you are dependent upon system designing. To learn system designing, you have to learn the algorithm. Okay, to solve algorithms, you should be very good at data structure. To learn data structures, you should be very good at OOPS. Okay, then to learn OOPS, you should learn any of these particular languages. So so this is the order of becoming an SD. Now what is the order of learning path? Okay, so you need to start from where there will be no dependencies. What are these here? So you should pick up at least one OOPS language, either C++, Java or Python. Then you should, after learning that language, you should go to the OOPS, then DS, then Algo, then SD, then like system design, then SD, right? So this is what topological sorting means. Okay, so before moving on to the any dependencies, okay, you should visit all the no dependencies, then only you can visit the dependencies. Okay, so I hope you got some good idea. Like I tried the best because it is going to be a good example. So, and these are all the few of the applications where topological sorting has been using. Applications are job scheduling algorithms from the given dependencies and among the jobs. Okay, ordering of formula cell evaluation in spreadsheets, ordering of compilation tasks to be performed in make files, and data serialization, resolving symbol dependencies in linkers. Okay, so it's very simple. Okay, it's very simple. Like if you haven't understood the above example, I can tell you the one as well. Let's say I have a given an statement like a result equal to x plus y plus z. Okay, so to solve this particular problem, first of all you require x, then z, then y. Okay, I can say that x equal to x into y. Okay, so for this again you require y. sorry, x, right? So I can say that x is equal to 2. Now again still you require y, so for y I can say that 2. Okay, now your x, you have solved the x, okay, you have the y. Now what about z? You still require z. Then I can say that z equal to y into r2. Okay, so you have y, okay, you have y and you have 2, so it is going to be, you have answered. So after getting all these things, you will be computing your result, right? So here, before moving on to solving the problem, you need to get all your dependencies done, then only you can solve the particular problem. So in whatever, like wherever such cases or constraints are exist, then you can use the topological sorting. Okay, I hope you have understood. Now I'm not explaining this code as of now, probably might be in another separate tutorial, because it will take a lot of time and it needs a very good amount of attention as well. So I will create a separate tutorial for this, where we will be solving 2 problems of topological sorting. And again there is a problem. Okay, so go through this problem. So this problem is called as an islands, number of islands problem, which is very good. Okay, we'll try to cover this in another separate tutorial. Now let's solve this particular problem. Yeah, heap data structure. Heap data structure. So heap is a special tree based non-linear data structure in which the tree is completely binary tree. Complete binary tree. I will tell you what is complete binary tree. So a binary tree is said to be complete if all the levels are completely filled except possibly the last level, and the last level has all the elements towards as left as possible, heaps of 2 types. So basically complete tree is something like this. Okay, so let's say suppose you have a root, okay, and you will be starting from the left first, okay, and then you will be going to the right, and then after this completing this right, again you need to start from the right. So it means like you need to follow the sequence. Okay, first you need to complete this, then this, then this, then this. You should not go something like this. Okay, okay, so here your right is empty, right? So this is not a complete tree, this is a complete tree. So which means that your left subtree should not be the empty, and the above levels are also not be empty. Okay, before moving on to the next levels. So then we can say that it's a complete tree. Okay, now we have heaps are 2 types, as I said, max heap and min heap. Okay, I will give you an overview of what is max heap and how max heap will be representing, and min heap. Okay, so in a max heap, the data element present at the root node must be greatest among all the data present in the tree. Okay, so they are saying that, let's say if I have a root of 100, then all my children's, okay, all my children's should be less than 100. Okay, so here like the root has to be good, like the root or parent node should have the greatest element among all the children's. Okay, here let's say here I have 100. Now I should have 90 here, and I should have a 99 here. Okay, and I can have a 5, and I can have 4, then 3, then 2, I can have 1 here. Okay, so here if you can see the parent nodes, okay, this is a parent, this is a parent, this is a parent. So parents are greater than the children nodes, right? Then this is called as a max heap. Okay, then you can guess what is a min heap, right? So a min heap will be having, it's an opposite. Okay, the root node, okay, like a root, okay, sorry, let's say 10. Okay, the root node will be the lesser among the all the children's it has. Okay, so here 10, so I can say 20, and I can say 30, and it will have a 40 and 60, and it is having 35 and 40, like sorry, it can have 50. So it should be like this. Okay, parent node should be less than its children node, then we can say this as a min heap. Okay, now I guess we are done. Okay, so this property should recursively true for all the subtrees. Yeah, they are saying that the smallest the root, okay, the parent node should be smallest among its all children's. Okay, now I guess we are done with all the data structures interview preparation questions. Okay, so for more such interview questions you can check out the interview blogs. Okay, you can find a hell lot of questions or which are specific to the language or framework or library. Please do check out the interview bit blogs. Okay, so that's it.